Okay, so we'll start with the initial spiel since we've got a couple of people here. Do you understand with everything with Silicon Dojo classes? I don't have kids. I don't want to deal with kids, so I'm not going to treat anybody like kids. So this stuff starts at like 6 o'clock. We'll actually start doing the class at 6:10. If you don't show up, I really don't care. It's up to you guys. So there's not going to be any of that. I do these, the attendance. 2 reasons I do the attendance is actually to be able to track people coming and how many flyers or whatever to print out, and also to remember people's names. For about the first 3 or 4 of these classes, I did not do attendance, and it was really weird to come in and see the same faces and have no idea who any of them were. So that's one of the reasons I do attendance. But if you can't show up, please just kill your RSVP so I don't print off stuff. Because again, we have like 42 people signed up for tonight, and I mean, this is a lovely group, but it's not 42 people. So anyways, if you are new, so Silicon Dojo, we have our main site, so we do all of our RSVPs on meetup.com, but we do have a main site, silicondojo.com. This will show all the classes and everything coming up. Do be careful for people, because I am starting classes again in Asheville. We're going to start doing more and more classes in Asheville. That's actually where I'm from. So if you do want to sign up for a class, just check where it's at before you sign up for it so you don't show up in the wrong place. So that's there. Again, for the new people, these in-person classes I actually do record in 4K, and I've got a little microphone thing here. So videos are here afterwards. We have fireside chats, and we do have self-study classes. These are entire programs that you can take basically at your own leisure, and these are some of the core technologies that we use at Silicon Dojo. This is all actually paid for through crowdfunding. So people ask, how does this get paid for? Again, it's free, basically what I call free to the end user. Free to the end user, not actually free. I'm paying $150 for my hotel room tonight. It does cost me money to do this stuff. Basically, people are kind enough to throw money into the bank account, and that's what pays for all of this. So if you click on this little support Silicon Dojo at DonorBox, that will give you this link, and then you can throw some money in. Now, a lot of people ask, that's cute and all, but is that actually viable? Again, we've only been doing this for so long, but this is actually what I pulled in for 30 days off of DonorBox. So this is becoming we'll call it a viable. It's in the black. It's in the black. So anyways, but any money you can provide would be lovely. With the money, again, education and money are abstracted. At no point in time will how much money you offer me actually come into education, mentorship, or anything else. It just pays for hotel rooms and gas. Let's see here. Again, everything is on Meetup. These are the classes and things coming up. If you don't know about it, there is going to be an All Things AI conference, March 23rd and 24th at the convention center here, just a couple of blocks away. If you pay for tickets, it's $200 for 1 day, $300 for 2 days with workshops. But the people that run that are incredibly kind and nice. If you don't have money, or you don't really want to pay, you can beg them for a free ticket, and they will give you a free ticket. I am doing a session there if you're interested. I don't know, there's a lot of stuff going on. I'm just saying I'm doing it if you want to show up to that. And the final thing here too is all of the documentation for all of these classes is on GitHub. So you'll see these are all the classes we've done so far here in Durham. Basically, you can click on that. That will give you all the code samples. That will give you the workbook. We use LibreOffice. So if you want to edit yourself, it's LibreOffice, and then it's in a PDF file. So all of that exists there. And yeah, any questions up until that point in time? Oh, look at these late people. Come on in. Let's see here. Bop. Here for TCP IP. Cool. Here's a book. Paper is yours, book is mine. Your name is?
Alan Salinger.
Alan Salinger. Cool deal. Oh, yeah, first one.
Finally attended in person, man. Been following your stuff for like 13 years.
Holy shit. Fair enough.
Hi.
Hello. Your name?
Somaya.
Bish. There you go. Cool deal. Paper is yours, book is mine. So if you want to scribble on it, take it, feel free. Yeah, do remember too, when you're looking at these books, one of the reasons I'm so free with the paperwork is this is all beta. Like literally, I stopped writing this class yesterday, so I have no doubt there's a whole bunch of problems in this. So this copy will literally never be used again, even if you don't take it. So again, feel free to take it. Okay, so let's talk about TCP IP and AI and why it matters. So the first question that's going to come up is, okay, we're talking about TCP IP version 4 and artificial intelligence. What do the two things have in common? Are you just AI washing? Sort of. Just so everybody here knows, AI is the cool new thing. I don't really care. I've been doing technology for 30 years. I started off in the Army in electronics, MCSE, NT4, the whole 9 yards. Basically, the way I look at artificial intelligence is that this is just another stack. Again, Joan has been in a lot of these classes. We build. This is actually the last thing that I did here a couple of weeks ago, diagramming everything out. So this was actually a Twilio voice AI system. And the interesting thing is if you look at a lot of this stuff, you know, you got Cloudflare, you got Nginx, you got Bottle, you got Python, you got RAG, you have Twilio over here, and then right here is your LLM, right here is your artificial intelligence. And that's what I want you to understand is artificial intelligence is simply a piece of functionality in a stack. Right? This is the overall stack. The overall stack is still using TCP IP. It's still using back-end programming languages. It's still using databases. It's still using all the crap that we've been doing for the past 20 years. We just simply throw in this LLM or model here, and it adds a whole bunch of capabilities to it. So one, yes, we are AI washing TCP IP version 4, but also TCP IP version 4 matters a lot if you're going to be building an AI stack. One of the things I want you to be thinking about right now, when you go out and you listen to people who are talking about artificial intelligence, it's interesting. Doing these commutes here, I commute 3.5 hours from Asheville. So I've started listening to podcasts. I never listened to podcasts in my life until I started doing that. And I've started doing the elliptical machine because I hurt myself and I can't run. So I'm on the elliptical, and I'm doing 3.5 hours of driving. So I put on these podcasts. I'm like, I'm going to listen to artificial intelligence podcasts. I'm going to listen to Sam Altman and the Anthropic people and A16Z I listened to today. That's Andrewitz, Horowitz, whatever. And listen to what they have to say. One of the curious things is when I listen in the modern world of technology where these people talk, they sound more like, again, if you're in the YouTube world, the social media world, they sound more like Steven Crowder or Sam Harris than they sound like Bill Gates. And again, it's an interesting thing. Like if you listen to Bill Gates, again, he was an ass back in his day. He was his own kind of ass back in his day. But if you listen to Bill Gates, you listen to Michael Dell, you listen to Ballmer and even Pichai and Nadella not too long ago, like they may have been complete and utter asses, I'm not saying that, but it was in the world of technology. Like they explained things and then they lied, but it was in their own little world of technology. One of the interesting things is when you listen to a lot of these AI founders now and the CEOs, it's these weird conversations. Like I was listening to this dwarfish guy and the Anthropic person, and they were talking about like the cost of infrastructure, right? Because Sam Altman and these other people want trillions of dollars of infrastructure. So this guy, this podcaster is trying to drill into him, and it's like, well, how do you rationalize $2 trillion in AI infrastructure? Because this is just an absolutely insane number. And the Anthropic guy is like, well, if we cure disease, is not $2 trillion a drop in the bucket? And you're like, but that doesn't mean anything. It's like, if I have a goose and it lays golden eggs, then it's worth $1 trillion. Have you ever seen it lay a golden egg? No, but it could, right? And we're in this kind of weird world. And why I bring that up is because language basically steers how you build things and how you do things, right? If you think about John F. Kennedy, right? There's two organizations that he created, right? He created the Navy SEALs, right? And so when people think about empire, they think about the Navy SEALs, big guys with big guns and body armor, you know, jumping into dangerous places. Grab a seat, wherever you can find a seat. And they think about that as empire. But one of the curious things is if you really think about it, the SEALs are pansies. The real people that support and drive empire was the Peace Corps. You don't really think about it, right? One of their main priorities was ESL, English as a second language. If I can get you to speak my language, the argument's over, right? Italians have 50 words for love. We have 500 words for pretending that we are valuable to our investors. right? It's a different way of thinking about things. And so why this comes up and why this is very important and why this all comes back to TCP IP version 4 is especially with a lot of coders nowadays, right? Coders for the past decade have been building things on platforms as a service. So if you're new to the tech world, you have software as a service, that's Salesforce, HubSpot, whatever, that kind of thing. And basically platform as a service is where you have this general platform that you can put your code onto it. Think about it like a web hosting platform, right? You put your PHP code, you put your CSS, you put your HTML, and you don't worry about CPUs, you don't worry about anything else, it just does what it does, right? Well, if you look at it, with a lot of the stuff with the JavaScript and a lot of these other things that we've been deploying, basically we've been deploying to platforms as a service, and so we're connecting things within these platforms in their own special way. Again, if you're using AWS, if you're using Azure, that type of deal, you're having this stuff connected. And so basically, that locks you into a paradigm for how you're going to be building your architectures, right? If everything is built in the Azure world, and again, if you've dealt with Microsoft, Microsoft has their own language. They have Microsoft for as a second language, right? Anyway, but again, you get used to that world. I was an MCSE. I remember coming out and dealing with Linux and dealing with Mac. And my whole thing was, but how do you do this? Like, because I was taught that Windows was the right way. Ergo, everything else needs to have a version of what Windows has. And it took me a few years to break that thing, right? So the cool thing about TCP IP version 4, especially if you don't understand what TCP IP version 4 is basically this is the networking protocol that allows your systems to communicate with each other regardless of where they're at. So you can build your platform, and your platform can communicate with servers inside your physical building. It can communicate with servers in other physical buildings that you own. It can communicate with servers up on things like DigitalOcean and Linode. It can communicate with AWS. It can communicate with Azure, and it can communicate with all kinds of different integrations and that type of thing. And so the big thing to be thinking about with basically with TCP IP version 4, even if you decide not to use it at the end of the day, is basically this is a protocol, and once you understand it, that allows you to think about designing things in different ways. And a couple of people came in. Let me just give them books so they're not lost. 1, 2. Da-da-da. Here you go. I'm sorry, what's your name?
Cyril. Here.
That one. All right, go on now. Hey, your name is?
Rennie.
Rennie. Cool. Paper is yours, book is mine. Feel free to scribble, take, whatever. Just leave the binder. Okay. So that's where we get into page 3 of the TCP IP book. All right. So again, why does TCP IP matter to coders and to artificial intelligence? It's architecture, 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 architecture. Of course, another person comes in. Anyways, I'll get you a book in a second. And this is going to be one of the big things. Again, like there's this weird thing going on in the AI world right now with vibe coding. And what you hear so much is this whole idea of you don't need to be here now. I mean, you need to figure out how to do something else. Maybe a bricklayer. That'll get you a retirement fund, right? That's what we're told, right? As technology professionals, the job is over. I hear that so often. Eli, why are you bothering with Silicon Dojo, regardless how much money you're making? I mean, this is just a dead end at the end of the day. But the big thing to understand, again, is that this is where we get paid. This is where I've always gotten paid. Again, whether I'm an MCSE or whether I'm writing code or whether I'm doing telephone systems that I did back in the day or surveillance systems or access control systems or any of these stacks, right? You design everything, how everything is going to get built, and then basically you just slap stuff together, right? The value is not writing code. The value has never been racking servers. That's the value. And then the company just doesn't have enough money to hire dog's bodies, so you end up doing it, right? But again, it's don't focus on the wrong thing. And so basically, when we look at TCP IP version 4, you're talking about the language of the internet. Basically, it allows everything to communicate together. There you go. I'm sorry, what was your name again? Carlo. Carlo. There. Okay. So let's look at a couple of examples talking about this. Again, architecture. And this is one of the big things. So I got into a snip fit with a clone of YouTube a few years ago, and then they died. Oh my God, I was so surprised. Anyways, the interesting thing with that is they decided to build their entire YouTube clone on AWS. Again, this whole idea of getting locked into an infrastructure. Now the thing is, when you're going to be building your infrastructure, you need to think about the cost of resources. Where is the best place to place your resources? When you look at the cloud, when you look at infrastructure as a service, which is what AWS or Azure is, compute and database, winner, winner, chicken dinner, right? All day long do your compute and your database up there, as long as you don't have any other reasons not to do it, right? The price point for compute and database is just dirt cheap. The problem where you get into is data storage and bandwidth. That stuff will kill you in a heartbeat, right? And so that was with this particular clone. They decided that they were going to be a clone of YouTube. And so being a clone of YouTube, they wanted to be able to distribute high quality videos, 1080p videos. 1080p videos are about, 3 gigs in size. And basically to stream a 3 gig video is about 3 megabits per second at 1080p. Well, the thing is, if you go to AWS, and these prices are about the same, they come down with scale. Basically, it's 9 cents per 1 gig output out of AWS. So that means if somebody streams a 1 hour 1080p video, that is costing you 27 cents. 10 is $2.70, 100 is $27, 1,000 is $270, and 10,000 is $2,700. And the interesting thing when you go to with AWS is they just keep billing you until your credit card runs out, right? So again, if you get a viral platform, everything can go to hell. And they, again, this particular, whatever the company was, I do forget what it was, they literally burned through $10 million in about a year and a half. And I just wanted to scream, right? And why the architecture matters is because a co-location facility. So when I started doing my videos way back in 2009, I put all of my servers into what's called a co-location facility. Prices on things have come down significantly. Basically, you could build a decent streaming server right now for $2,000. Looks a co-location rack nowadays about $200 per month per U with a 1 gig fiber connection, right? And the thing with that is you get that all day long. You do have the upfront cost of $2,000 or however much for the server. You do have the monthly cost for that rack, but that's it. If you sign a contract for $1,000 a month, you've only got $1,000 a month, right? And so that's one of the things to be thinking about if you're trying to compete with YouTube or whatever else, is thinking about how to allocate those costs, right? If you're putting things storage online with infrastructure as a service, the costs are going to go up dramatically as soon as load goes up dramatically. Whereas if you put your own stuff in a co-location facility, there is one upfront cost, but it basically stays that way forever. And again, with 1 gigabit per second, if you're looking at approximately 3 megabits per second per 1080p stream, you're getting 300 concurrent video streams for a 1 gig connection for $200 a month. And again, this is the kind of stuff you need to be thinking about with the whole architecture deal of where do things actually make sense. And that's with TCP IP, right? This is where you can figure it out. It's like, okay, maybe I'll put the stuff in a colo facility, maybe I'll put it up on AWS, maybe I'll do some other things. I will say, if you ever do try to create a clone of YouTube on AWS, their prices just get wacky. Again, you have to be careful with this when you're designing. So I found this out the hard way. I went with a hosting provider. So I had my stuff in a co-location facility for a while. Then I went to a company called Bits on the Run. The weird thing with Bits on the Run is they charge you whatever amount, but they were using AWS. And so the curious thing with AWS is AWS charges, so they have what's called a content delivery network. So a content delivery network is basically your video goes to a hub, anybody in the area then connects to that local hub for decreased latency. So it's 9 cents to the hub, to the content delivery network node, but then past that it's free. Right? That seems like a good deal. Except you're me, and it's 14 years ago, so I've got 1,000 viewers instead of 1 million viewers. And so here's the thing, you don't get any value from a content delivery network if every one of your viewers is spread all over the world. So basically every time a video streamed out, it always went to an entirely different node, and therefore my bills went through the roof. So some of those random things to be thinking about in the real world. When we start talking about this with artificial intelligence, the things to be thinking about right now is going to be data sovereignty. If you're not thinking about data sovereignty right now, you need to be thinking about it, even if you don't have to. Basically, what data sovereignty is for a lot of countries, right? They want their data to remain inside the country. There's this weird idea that if I can see the data, somehow I can control it. And it's too hard to explain it to the politicians. That's not how it works, but that's how they think. So one of the interesting things with TCP/IP is there's something called Geo DNS. And so we'll go into this in a little bit. So DNS is resolving a domain name, cnn.com, to an IP address, 88.65.25.2, right? So one of the cool things with Geo DNS is depending on where the user is physically located around the world, it will resolve to a different IP address. So if I'm in Vietnam and I go to elisai.com, it will resolve to a server that's in Vietnam. If I'm in the United States and I go to elisai.com, it will resolve to a server that's in the United States. And again, that's some of the stuff you can think about from an architectural standpoint that's just kind of seamless. The users don't even see it, so hopefully they don't notice and they don't try to hack your system and get you in trouble and all that kind of stuff. So that's some other stuff to be thinking about. Any questions with that kind of thing? No? Okay. Then we get to page 4. So you're going to hear these acronyms: LANs, WANs, MANs, CANs, GANs, and the internet. So when we start talking about TCP/IP version 4, the big thing about TCP/IP version 4 is it's called a routable protocol. So not all protocols are routable, especially back in the day when I was learning this stuff. Anyways, but it is a routable protocol. What that means is that basically you can section off your own networks. The idea was with this system is that we create all of our own little networks, and then we connect those networks together, and people are able to communicate. Right? So again, you think about the internet. The internet is basically, we have all of these networks. So in here, we are part of a network, and this network connects to the internet. The building across the way is a network that connects to the internet. Your home is a network that connects to the internet. And basically, that's one of the fundamental concepts of TCP/IP version 4 is that we're segmenting off all of these different networks. So when we talk about LAN as a local area network, it is this network. It is within what we call our subnet mask. Basically, it's just all the computers in this particular network that are able to see each other. You then get to WAN, which is called a wide area network. So think about this if you had a corporation, and so this hub office would be its own LAN. We would have a router that connects us to the rest of the networks, and all of those other networks together would be the WAN, right? So we have one office here, and one office here, and one office here, and one office here. These are 5 different LANs that are connected together as a WAN. Beyond that, you'll hear about MAN. These are actually coming back. These were cool back in 2000, and new stuff is cool again. MANs are called metropolitan area networks, right? And a lot of this is just logical. Again, sometimes, I'm slightly autistic. I'm an Aspie, so sometimes you give me definitions, and you're like, and like it's just logical. It's just an idea to give you an idea of what's going on. Basically, what a MAN is again, think about something like a government organization. Let's say the police department of Durham, right? They're going to have cameras. They're going to have a lot of different equipment that's going to be using TCP/IP version 4, hopefully. And the idea is a metropolitan area network, right? You have all of their different police stations. You have the corrections office. You have the surveillance cameras. All of that comes together into their network, which will be a MAN. You have a CAN as a campus area network. Again, same kind of thing. Think about your college and that type of thing. And then now, again, one of the new things to be considering in the modern world is a GAN, which is a global area network. So as companies become bigger and bigger and bigger, the idea is their private network starts spreading around the world. And again, you start having to start thinking about what the architecture of that whole mess kind of looks like. And then you have the internet. The biggest of them all is the internet. Any questions on that kind of stuff? No. The one thing, and we'll go into this because I forgot to put it in here. When you think about the internet, what's really curious about doing this class and talking about artificial intelligence is there was an amazing argument that I heard. Oh, this is hard. Again, almost 30 years ago at this point in time, that the first real artificial intelligence was actually the internet. Because it was the first true computer device that in the real world was doing things autonomously on its own, doing self-correction, and the whole 9 yards. So when you think about the internet, when you're dealing with this, because a lot of people don't think about this, we talk about the cloud. There's a lot of people out there that don't really understand what the hell we're talking about with the cloud. Always gets frustrating. I talk with normies, and I'm like, cloud, what's cloud? And like, oh. Anyways, we talk about the cloud, right? Basically, the idea with the cloud, right, is let's say we have CNN.com. So I've been using this example for 17 years. Gonna keep using the example, right? CNN.com, you know, they basically have their own web servers. They have their own SQL servers. They have their own, what are called, SANs, storage area networks. They have their whole system, right? When you go to CNN.com, there's a whole bunch of stuff going on in order to get that web page that makes you absolutely miserable for the rest of the day. So anyways, and then they connect to what's called the internet. You're on this side, you are in a building such as American Underground. There's a whole bunch of different computers here. There's switches, there's routers, the whole 9 yards, and then you connect to the internet. Now here's the thing, right? When you look at CNN.com's architecture, you can draw this out. As long as they tell you what the hell it is, you can sit here with a whiteboard and you can draw out all the SQL servers and routers and switches and access points and all that kind of stuff. Again, on this side, if you know what's going on, again, you can also draw out, we can do a network map, routers, switches, access points, and the whole 9 yards. The idea when we talk about the cloud, where the term cloud really comes from, is, so what happens here, Eli? It goes to the cloud. What does that mean? The cloud. Stop asking questions. Because basically, what's really interesting here is basically when you get into the cloud, there's lots of routers, there's lots of these things called interconnect and all kinds of tier internet connection services and all that kind of stuff. And so basically, when you go from your home to CNN.com, there are things called routing protocols. And routing protocols are languages that networking equipment use to basically try to figure out the path for you, right? And so basically, maybe you go to CNN.com the first time, and it'll send you through that path. It'll send you through those. But let's say this piece of equipment has a power outage, so the next time you try to communicate, it'll go this way, and then it's just easier to keep going down this way, and then it'll go this way. And then somebody turns off this particular router, and so the next time you go through, it goes here and here and here and here and here, here. And basically the idea is that when we're talking about the cloud, I don't know, it just hits the cloud. It's just somewhere logically not here, right? The idea is a physical device is that, right? This. This is not cloud. I can point to it. Right? It could be an email server, it could be a VPN server, it could be all kinds of different stuff. Where does this reside? There, right? When we talk about the cloud, we talk about this. And so again, when I started learning about this 25 years ago, we just talked about networking equipment and that type of stuff. Nowadays, again, you just have servers up in the quote unquote cloud. And we talk about servers up in the cloud, the idea is if you're using DigitalOcean, right, you have a server and you have a configuration, you have IP addresses and all that kind of stuff. You're like, great, but where is your server? Cloud. I have no idea where my DigitalOcean server is. It's just in the cloud. So this is what we're talking about when we are talking about the cloud, because some people do get confused with that. And the internet, that's basically the internet. The internet, just so everybody, again, for anybody who does not know, this is the internet. When we talk about internet, that is the network, basically the global network that connects all this stuff together. Then you hear about the World Wide Web, and it is important to understand World Wide Web is different than the internet. Basically, the World Wide Web is just all of the web pages that happen to reside on the internet. So voice over IP traffic happens on the internet. It doesn't happen on the web. That makes sense. Okay, any questions with that stuff? Oh, cool. Okay, then we're still on page 4. So logical versus physical. When we start talking about this stuff, especially in the TCP IP4 world, this becomes very important. So when we're diagramming things out, right? When I say, okay, you know, so we have this router, okay, and then under the router, we're gonna have a switch, and off of the switch, we're gonna have an access point. But you know, on top of this, we're kind of worried about, you know, security and traffic, and, you know, so let's put a firewall in here. right? So when I'm going to be diagramming things out in a TCP IP world, right, I'm going to be diagramming things out what is called logically. These are all different things. A modem is a thing. A router is a thing. A switch is a thing. An access point is a thing. A firewall is a thing. A file server is a thing. These are all logical things that I'm going to sit here at a whiteboard and scribble this stuff out. Those are the logical devices. And then you have the physical device itself. So when you go to Comcast, you go to AT&T, and you get your fiber modem shipped to you, right? You call it a fiber modem. Well, it is the physical device is a modem and a router and an access point and a switch and probably 5 other things I shoved in there, right? And so that's one of the things to be thinking about too when you're dealing with this kind of equipment is separating out the idea between the logical devices and the physical devices. So you draw out your architecture based off of the logic, and then you go out and you find the proper equipment and slap that together so it might look very different. Like, so basically on your diagram, you might have 7 different logical devices, and when you go to actually plug it into your server room, it's just one little box. So that's what we're talking about with physical and logical. Especially when you start dealing with customers and clients, this can be a real pain. Again, like technology people kind of throw around the word router, and so when you actually start talking with customers and they're like, but I have a router, and you're like, that's not, golly, that's its own thing. So that's the idea we're talking about when we're talking about physical and logical. Then we go to latency. So this is going to be a big thing to be thinking about with your network, and again, especially with TCP IP version 4, is basically the latency is how long it takes between a request from your computer to the response when it gets a response back, right? And how important latency is going to be depends on the protocol and the application. If you are doing FTP, file transfer protocol, you're moving a file from point A to point B, I don't care. I mean, my latency can be a second. My latency can be 10 seconds. I'm going to go have a cup of coffee. I don't care. It's a file. I'm moving a file around, right? Latency doesn't matter. Where latency becomes important is things like voice over IP, right? So if you ever do a ping test or whatever else and you get the latency back, basically, depending on who you're talking to in a particular day, at somewhere around 75 milliseconds latency, traffic between the 2 points, you are going to start noticing something called jitter for voice over IP. And what jitter is basically when you do a voice over IP conversation and people like weirdly start talking over each other. You ever have that where you're like, I'm not rude, but I'm really talking over this person all the time. But it doesn't really sound horribly off either. And the reason is because we're used to a 0 latency world. You're now getting over 75 milliseconds of latency. So you say something, the response comes back, and all of a sudden things aren't working out quite right for that communication. You start going up into some things like 200 milliseconds, especially with something like voice over IP, and then you get some more of this jitter where like the packets just don't sound right, like the voice is just really jumbled and everything kind of gets screwed up. So this is one of those things you're going to need to be thinking about with especially in the artificial intelligence world. So if we look at this for network latency, web browsing, sub 150 milliseconds is considered good, 150 to 300 milliseconds is considered noticeable, over 300 milliseconds is considered bad. So basically you're talking about over 1/3 of a second delay and people start noticing, right? People will click off web pages if it takes over 2 seconds to load. So if you're already burning 1/3 of a second just in the traffic, and again, with this latency, a whole bunch of things can build up, you can run into problems. Again, SSH and RDP, over 300 milliseconds can be bad. Over voice over IP, they say under 150 milliseconds good. I would question that, but again, you see noticeable. Then you see databases and this type of thing. Again, you start talking about databases, you start talking about database replication. This gets really interesting in architecture. So back when collocation facilities became a big deal, basically being able to rent your own server farms became a big deal. For database systems, a lot of corporations decided for resiliency and disaster recovery, they would put database systems in entirely different physical locations, and basically they would replicate. And there's something called high availability. There's a heartbeat signal, a whole bunch of stuff. Basically the idea, if one data center gets wiped out by a tsunami, the other data center just stays online and nobody notices the difference. One of the things that becomes very interesting when we start taking a look at architecture at this level is basically what they found out is that data centers could only be about 50 miles apart in order to maintain a low enough latency that the database systems could actually communicate with each other. So again, in that whole replication process, you need to have a latency below a certain level for things to work properly. And so again, actual physical distance mattered. And that's going to be one of the things too. Again, we talk about things like Geo DNS. The closer a server is to the user, by and large, the less latency there is going to be, right? So that's where they talk about, like with video game servers, that type of thing, they want it to be as close to you as possible. And so again, things to think about with latency, and again, that's where we talk about like Geo DNS and that type of deal. Why this becomes even more interesting is you start doing services like artificial intelligence, and you start thinking about your overall system latency. Right, so basically, again, last class we did here, we were doing Twilio. We were doing AI telephone agents. Well, one of the things to be thinking about with users is users get frustrated just because everybody's pissed off nowadays. Everybody's angry. They start at being angry and it only goes downhill from there. So they call your system. The longer it takes your system to respond, the more irritated they're going to be. So when you think about latency, not only are you going to have network latency, but you're also going to have your own internal system latency. So the communication has to get to your system, it has to process through the backend language, it has to get processed by the LLM, then something has to occur, information comes back, the LLM has to process a response, and then it has to ship it back to you, right? And so again, one of the things to be considering there is the overall latency in that communication process and basically how happy your users are going to be. And so that's what we're talking about with latency. Any questions on latency? No? Yep.
Why do databases need such short latency? Like, can they just like make the timeout like longer or something, or is there something that like the heartbeat needs to be shorter for some reason?
Yeah, so basically, when we talk about database systems, again, we talk about resiliency and clusters. So there's something called high availability, right? And basically what high availability is the idea is you essentially have 2 or more clusters of these database servers, and you want to maintain the highest uptime for the users as possible. Why the latency matters is because those database systems are constantly replicating with each other. So basically, as people are doing writes in the database, in order for it to work properly, basically both database systems have to be the same. You can get something, God help you, I've never had to deal with it. It sounds absolutely horrible, called split brain. This is a real thing, where basically you're supposed to have a high availability, 2 high availability systems, and they become different. And yeah, nastiness can ensue. So yeah, basically the idea with the database systems is that they're communicating back and forth, replicating that data, so that if one system goes down, again, I was in Asheville, I was there for Helene, you don't expect the biblical flood until you're looking at the biblical flood. And so all of a sudden, your data center goes away. The idea with high availability is your users don't, again, this is not a backup system. This is not, it just does its thing. And then you all get together for a cup of coffee and talk about the misery of your life for the next 6 months. And again, that's one thing to be thinking about in the modern world. We call it disaster recovery now. It used to be backup systems. With disaster recovery now, the idea is the user shouldn't even notice what happened. Basically, all hell breaks loose. Your life is going to be miserable. You wonder how good the relationship is with your spouse. And all of your users are just like, da, 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 I hate my job. Right? Anyways. It used to be, again, with backup systems, everything would fail, and you came in and rebuilt everything. Yeah. One of the big things to be thinking about nowadays, anytime, is when you're dealing with TCP IP, any computer system, beware of caching. IPv4 loves its caching. One of the things when you're dealing with TCP IP version 4, remember you're dealing with a 50-year-old protocol. So protocol is this language This should have died so many years ago. So many years ago, IPv4 should have died. And so a lot of things that were built into IPv4 made a hell of a lot of sense in 1985. You're like, wow, 1985? That's smart. Right? Again, it's 2026, this stuff should have died, but it's still there. And so one of the big things in the TCP IP version 4 world is, with kind of like this resiliency thing in mind, the idea is, what happens if you can't communicate with a server? Again, what if there's just blips on the line? Like, not the server didn't crash, there's no biblical flood, just blips, right? The idea is that your system should be able to stay up and running. And so how that happens is, when your systems communicate with other systems, when the response comes back, the response will be saved at least for a limited amount of time. So that if it can't communicate with the server again, it will just use that local cache as whatever the standard is. The problem that you run into is, you being a nice technology professional, you sit down, you do all of these changes for configurations, you go, great, you go to test it, and nothing works properly. And the reason is because the cache saved all of the old data, and so your computer is using the old data. You just spent half an hour changing configurations, and the computer doesn't care, it's still using the old crap. So you'll see like flush commands, like for DNS, there's something called DNS flush, and that basically flushes out something called the DNS cache. There's other ways to flush out caches, so that's one thing to be careful about. Again, one of the big things that new technology professionals run into is, when they spend like 5 hours rewriting the exact same code, because the code was fine, it was just using cached information and you didn't realize it. So do be careful of caches. Let's see here. Let's talk about the OSI model for a second. So this is going to come up as we go through the class. How many people here know what the OSI model is? A couple people. There you go. So basically, the OSI model is a logical model. I've heard an argument nowadays that it's 2026 and you shouldn't learn the OSI model anymore, and I have no idea what the hell anybody's talking about. Basically, this is a lifesaver. Like, as a real technology professional, like, hug this. Learn it, love it, live it. It's wonderful. Because basically what the OSI model is trying to do is, it's trying to break down all of these components of network communication so you can figure out what the hell we're talking about. Right? Because one of the big things is, when you're dealing with large systems, again, it's broken doesn't help anybody. Right? What you need to do is, you need to try to figure out what in this system is broken. Again, remember, when you're dealing with large systems, this stuff might be geographically diverse. This stuff might be, other people might be responsible for equipment. Like, you may think there's a problem with a piece of equipment, but you're not allowed to touch it. Like, when I got my first corporate job, again, talk about the real world, bizarre crap in the real world. So my company, they pay for all kinds of training. So I got sent out to Denver for Cisco training, went through the CCNA training. They spent a week, they wined me, they dined me, they put me in a great hotel. It was just an absolutely lovely time, right? Anyway, so I get back to my home office, and I was responsible for about 12 offices throughout the Northeast region. I called the Datacom folks back in Denver and say, hey, I got back from the CCNA training, give me the usernames and passwords. And they said, no. And I was like, what? And literally what I was informed, because my company was actually pretty decent, they said, look, if a tsunami hits Denver, we want you to have the knowledge to be able to configure the networking equipment until we figure out what to do. Until a tsunami hits Denver, you're not allowed to touch that crap. So one of the problems you run into is, when you're troubleshooting, right? Is it your server? Is it the device? Is it the wiring itself? Or is it this equipment that you're not allowed to access to? And so basically what the OSI model does for you is, this is a logical model that's used so that you can start trying to diagnose more or less where the problem is. Right? So one of the things you're going to hear in life is, it's always a physical layer. It's always a layer 1 problem. Whatever problem is, layer 1. You say that, you will win the bet 99.99% of the time. So layer 1 is basically the physical connection. The network cables themselves, 99% of the time they unplugged it. I literally had to fly out to an office. The person said, our main computer's down. I was like, okay. I was like, oh, look in the back, make sure the cable's plugged in. Oh yeah, the cable's plugged in. I'm like, shit, really? Yeah. Okay, I called the travel department, flew all the way out there because it was my responsibility. I get there, I look behind the computer, I go click, it's on the network. Real world, real world. Anyways, so physical. So we're talking about network cables and that kind of thing. You then have layer 2, which is called the data link layer. These have what are called MAC addresses, media access control addresses, we'll talk about in a second. And this is a layer for switches. So basically if you go into your network closet and there's some kind of networking device that has lots and lots and lots and lots of ports on it, that's going to be your switch. That's going to be your layer 2. Then you have the network layer. That is going to be where your TCP IP resolves. That's going to be with your routers, again, IP addresses. Above that, you have transport layer, then you have session layer, then you have presentation layer, and then you have the application layer. And so basically, again, we're not going to get horribly into this today, but as you start to understand more and more of this, you start to understand where the problem is. So again, like the session layer, 99% of the time it's a physical layer, 1% of the time it's going to be the session layer, at least how it used to be. So like one of the things with a lot of server software that you install on premises is when you buy it, it will give you so many seats, right? It'll give you 2 seats, 4 seats, 10 seats, however many seats, right? And basically what those seats are is how many concurrent sessions the server is able to have with client computers. And so basically what you'll go through and you'll troubleshoot and you're like, okay, I can ping and I can see the computer and all this stuff that doesn't work, but for some reason this particular program isn't working properly. And basically 99% of the time your user is DDoSing himself. Like I saw this again in the real world. I had one of my clients, they had the specialty piece of software that a few different people had to use. They had 4 concurrent sessions on it that they paid for. The problem was some people, again, this was Windows XP era, sometimes people would open up the software and then they would go to lunch. And so then the screensaver with the lock screen would come on, but the session was still active, ergo nobody else could get into the system, which was kind of fun stuff. So anyways, when we're talking about the OSI model, again, this is just a logical model and it's a way for you to think things through. You'll hear about the TCP IP model, and a lot of people love the TCP IP model. Again, 18-year-olds love the TCP IP model. Why? Because it's 4 layers. It's easier to pass a test on. It's like, why do you like it? Because I passed the test. And you're like, oh, yeah, but this is our job. So anyways, 7 layers of the OSI model. Any questions there? No, okay. Then we get to protocols. So when we start talking about protocols, we get a little focused on things like TCP IP version 4 or IP version 6 or whatever else. Basically, when we're talking about protocols, we're talking about simply a language that the computers use to communicate with each other. So we talk about a networking protocol. That is what we're doing tonight, TCP IP version 4. There used to be a lot. When I tested for this, we had to learn like 10 of them. Now you just learn IP version 4 and you're done with it. So there used to be something called IPX SPX, there used to be NW Link, there was something called AppleTalk, there was NetBEUI and NetBIOS. Basically those are networking protocols. Generally, unless you're really high up in the corporate world and doing something really weird, you're just going to be using IP version 4. But you will hear about different protocols out there. So things called routing protocols. So that's what I was talking about before with the networking equipment. And so this is the language that your networking equipment uses to talk to each other, right? Your routers and your switches, they'll communicate with each other just to make sure there isn't a disaster. So I don't know, we used to use RIP. There's something called OSPF, Open Shortest Path First. Whole bunch of different other routing protocols. You also have things like storage protocols. There's something called iSCSI. There's new ones out now. Basically, if you're going to basically attach storage onto like a network type device, you use that kind of protocol. Then you're talking about communication protocols. There's SIP, there's RTMP. There's a whole bunch of those different types of protocols. So basically, when we're talking about protocol, this is just going to be a language that is used for computers to be able to communicate with each other. And that's where we get to TCP IP version 6. Where is it at? Tomorrow is always a day away. The funny part about doing these classes is I've been doing these classes for 16 years now. And this joke only gets funnier as time goes by. So real story, lived experience. So I got my MCSE in 2000, something called NT 4.0. My boot camp that I was going through, they really wanted to give us as much as we could possibly have on our resume. So we had to pass like 7 tests. And so they realized that if we did this thing called the TCP IP version 4 test, that would give us the plus I. So I'm an MCP plus I because I took that particular test. And I still remember my instructor in 2000. And he said, you know, I want to apologize to all of you. It's like, look, we're gonna have you learn this information for TCP IP version 4, and we're going to have you take the test because we think it's going to be best for your resume. But to be honest with you, this is all going to be gone in about 2 years. 2 years, IPv4 is just going to go away. There's something called the IPv4 network addresses. There's about 4 billion of them in the world. We are going to run out by 2003. They've got to be gone at that point. So we're gonna be off of IPv4 and gonna be onto this thing called IPv6. Yeah, I told that story back in 2009. You can go watch the YouTube video where I told that story in 2009. We're now in 2026. Yeah, IPv6, basically it's a protocol. It builds on IPv4. So basically, again, we'll talk about it in a little bit. TCP/IP, IPv6, v4 is actually a protocol suite. TCP is one protocol, IPv4 or IPv6 is a different protocol. IPv6 is fine. IPv6 was a modern protocol 30 years ago at this point in time. But it's kind of one of those things, we talk about legacy, right? One of the big things I talk about in the world is once you install anything into your network, it will never go away. It'll be like it just is there forever. And that's basically what you get with IPv4. It works good enough, and so everybody keeps using it. But one of the things to think about in the modern world with communications, so many of the problems that we have today is we are using a protocol that was literally designed for 50 years ago. Again, people talk about security, they talk about anonymity, they talk about all of this stuff, and it's just like, it's great. It's just IPv4 wasn't built for it. I mean, it just functionally wasn't built for it. Basically what happened, long story short, again, how the technology world really works, everybody thought we were going to go to IPv6 because we were going to run out of IPv4 network addresses, and then basically something called NAT came out. It's called Network Address Translation. Basically, again, we are in this building, we all have internal IP addresses here, we connect to a router, the router has NAT in it. Basically, there is an external IP address on that router. We all are able to share that external IP address, and that router keeps track of all the communication. So now we can have gazillions of IPv4 computers running when there's only 4 billion addresses available. The other thing too, again, everybody talks about artificial intelligence, and this is one of my big, pet peeves that I talk about a lot if you've come to my classes, is the technologies that fundamentally change our entire world nobody knows exists. NAT. Our world would not look how it does today if NAT didn't exist. Good or bad is a big question. Nobody has any arguments about NAT. It's just one of those weird things in life. And again, that's where I talk about things like with artificial intelligence. That's why I get a little hairy with AI, is everybody's talking about AI. Like, no, Norman, you are never gonna go home and have your mom give opinions on NAT. I really think proxy servers was a better way to go. This whole NAT thing, they're never gonna do. But again, AI, they won't shut up about for some reason. Anywho, then we get to the Ethernet standard. So we're going along the path for the TCP/IP version 4 world. So when we talk about the Ethernet standard, that's the networking that we're using. Anytime you plug your computer into a network nowadays, it is going to be Ethernet. Now, Ethernet is not TCP/IP. It's the paradigm for doing networking. Again, you go back 25 years, there's a whole bunch of different ways of doing networking. We all now do Ethernet. Basically, when we talk about the Ethernet standard, it just has a few standards here. Star topology. So basically, all the computers kind of connect into a hub, and that's what we call a star topology. We're going to have an introduction to networking class later. I'll talk about this a little bit more. Use something called RJ45 connectors. So those are what look like really big telephone connectors to connect. You have these things called MAC addresses. So MAC addresses are actually built into the Ethernet standard. This is not actually part of TCP/IP itself. And then one of the important things, and this is going to come up later, is how communication operates in the Ethernet standard. So this is the Ethernet standard itself. It's something called collision detection, collision avoidance, which again is also a really bad way of doing things in 2026. What happens here? So back in the day when they were trying to figure out how all these devices were supposed to communicate with each other, because again, remember with any technology, somebody like you was sitting around with a beer having an argument with somebody else that they lost, and then they did what the other guy said, or the girl said, right? There's all these different ways things could be built, but then somebody actually has to build it and scale it and ship it and replicate it and the whole 9 yards. So anyways, basically you used to hear something called token ring network. And with the token ring network, it was interesting for communication. So you had all these computers that were basically on a ring, whether or not it physically looked like a ring. And there was a token. There was actually a token. There was kind of like a token that moved around. When one computer got that token, if it wanted to communicate, it would put its little payload into that token. It would go to the computer that the communication was meant for, and then it would dump off the load. And then if that computer had something to say, it would take the token. And basically, you had this token, digital token that was going around. Computers would only communicate if they actually had the token. There's good parts to that, but there's bad parts to it. So basically, with Ethernet standard, the idea was we don't like that. So what's going to happen? We have a much better idea. You have this thing called a hub. So a hub is basically like a splitter in the Ethernet world. And so you have all of these computers that are connected to a hub, right? And so what happens is if this computer wants to talk, it'll listen on the line. It'll listen. Is anybody else talking? Nope, nobody else is talking. So it'll send its communication down to this person. Right? This person will listen. Anybody else talking? Nope. It'll send its communication back. Well, the thing is, let's say this person is listening and this person is listening. They want to send at the exact same time. Nothing is happening right now, so it's clear. So they then send their communication to whoever they want to send their communication to. One person sends communication, the other person sends communication, and then you have what is called a collision. Those not packets. Those frames basically collide, and when they collide, you have a little explosion on the line, and that gets detected by the computers. Basically, they will then wait a random amount of time, listen again, and then try to send the communication. So this is what's called collision avoidance, collision detection. Again, you have 4, 5, 6, 7 computers on something called a hub. It's not great, but it's probably not going to crash anything. How many computers do we have in this room right now? Right? You start having real problems with this particular network design style. We're going to talk about that in a second with switches and bridges. But that's one of the big things with the Ethernet standard. It's the whole idea. You'll hear the concept of collision domains. You'll even hear this in the Wi-Fi world, collision domains. And that's basically all of the computers basically within this particular network where their communications might collide with each other. We started to see this a lot in the Wi-Fi world for wireless, probably about 2010. Again, as more and more Wi-Fi devices got into the network, that's when you started to have problems where you had 30 Wi-Fi devices trying to communicate with a wireless access point that could only support, let's say, 10 users at a time. You ran into a whole bunch of problems. Thankfully, it's 2026, so that problem went away. Okay, so any questions there? Yes?
Will IPv4 ever actually go away, or do you think it's here to stay? I mean, I guess maybe it'll get some point.
Well, I mean, we'll all burn up in the sun at some point. Yeah, I don't know. So like with IPv6, to be clear, IPv6 is now being used. Many websites, Google, Facebook, they now support IPv6, which they didn't even 6 or 7 years ago. When you're using your smartphone, these actually use IPv6. Again, the weird part you get into is we're so addicted to IPv4 though. Like with IPv6, there's something called IPv4 tunnels, which again, so basically you can connect two networks using IPv6 and you tunnel IPv4 inside that IPv6 connection to give you IPv4 communication. So at some point, I don't know. Yep.
I have kind of like a follow-up question on that. So like, like every house probably has like the public IP, right?
Yep.
Like, are we at anywhere close to running out of public IPs? Like, obviously we have the NAT for all the public, the private, or like.
Supposedly, so all these IPs basically got sold or leased in blocks. So that's the thing. They weren't leased individually. So there's like 4 billion of these. Again, we'll go into blocks a little bit. And so again, back in the 1980s, 4 billion seemed like, who's ever going to use 4 billion? So a lot of these blocks were basically sold off. And so all the blocks, or almost all the blocks, are entirely gone. It doesn't mean all the IP addresses are actually being used. So basically in the IPv4 world, what happens is when your router, your modem connects to the internet, there's something called DHCP, Dynamic Host Connection Protocol. What this does is it dynamically gives you an IP address. So this is where you'll see, like if you want to be real techie, you'll buy a static IP address, and now they cost you like $5 or $10 a month to get an IP address, and that gives you an IP address that you keep. For most people, what happens, you have a DHCP address. And so basically they have a pool of these addresses, and they're able to kind of feed those out as different networking equipment comes online or offline. And so that's basically how they deal with it now. Yeah. So yes, technically I think we ran out, was it 2000, I don't know, you keep nodding your head, 2016 or something they ran out, somewhere around there. What's that?
I think that might be what sold in the last box. They were like up for grabs.
Yeah.
Then still even corporations who have security teamwork like ICANN.
Yeah.
There are people who will argue about that in companies.
All right, there you go. Okay, so now let's talk about media access, media access control addresses. So MAC addresses, this is gonna be one of the big things. So again, and this is one of the things I find funny in life, and this is where you just get tired of normies at the end of the day. So one of the things everybody's worried about, have you heard? Trump is gonna do it, or Biden was gonna do it, or Obama was gonna do it. They're going to fingerprint all of our computers. They're going to put an identifier onto every single one of our computers so they can track us. It's like, yeah, they did in 1975. So basically, when you look at a MAC address, most people don't even know these things exist, which is why they don't talk about them. So again, one of the things you have to think about in the technology world, again, when you start building things, is identity becomes very important. We talked about this in the class for SQL that we just did. Like, there always has to be a unique, right? Because if you have two duplicate identifiers on the network doesn't know who to send the communication to, right? So you have to have a unique identifier. So the idea with the MAC address is, yep, that is a social security number for your network device, right? So what the MAC address is it's supposed to be a globally, absolutely, universally unique number. The first part of it is supposed to be the vendor ID. So basically who produced the particular equipment. And then the other half of it is supposed to basically essentially be their serial number, right? And so basically every single device has a MAC address. And so we can go to, let's see here, Control C, Control V. You can go to a site such as this, macvendorlookup.com, and basically you can plug in a MAC address and it will give you who the vendor is. So if I go to our particular document here, I can plug this in, Control C. Oops. All right, some lady in a car, and I can just simply plug this in. Okay, so here, see, right, by this MAC address, it can basically tell me the vendor for this particular MAC address. Apple Incorporated, this is most likely what their address is, and here's the range, right? Because all of this stuff is just kind of stored in a database type system. And so the important thing to understand about the MAC address, again, this is hard-coded onto each individual network card. So this would be for like my wireless card here. And basically it's used as that absolute unique identifier. And so MAC addresses are there. And again, that's one of the things to be thinking about when you're getting tracked in the real world is on the internet. So when you go to the internet, your MAC address more or less can't be tracked unless they're doing something whack, right? So on the internet, you're fine. But here's something to think about. Every time you connect to somebody's network, they can collect your information. So when you go to a hotel and you connect to the hotel's Wi-Fi, they can grab that MAC address and then they can start identifying you based off that MAC address. So they could track you, right? So if they grab that MAC address in your hotel, and then you go to a cafe and they grab the MAC address, and then you go to an airport and grab the MAC address, and they go to any time you connect to a network, they can grab that identifier, and if they can point it back to you, they can literally pinpoint how you go through the world. So again, your fears already exist. Yep.
I wouldn't consider MAC address as a unique identifier. I think the UID is probably more unique because you can spoof MAC addresses.
You can. Well, you can clone a MAC address. So again, with any of this stuff, yeah, there's something called MAC address cloning. You are correct. That'll be a different class. Yeah. But yeah. Yes, if you're smart enough and know what's going on, you can clone this. The important thing is to understand that that exists. So like MAC address cloning, like with that, so like with Comcast, I don't know if they still do that. If you went out and bought your own cable modem, Basically, the security Comcast used to have for their ISP was the MAC address. The MAC address was in their system. If the MAC address was in their system, they allowed the internet communication to happen. If the MAC address wasn't, they blocked the communication. That was their security thing. So you would clone. So what would happen is they would give you a MAC address. You would go into your cable modem, plug in the MAC address they had told you, and that was called cloning the MAC address. Again, that's its own world. The important thing in TCP IP that the MAC address exists, and that kind of thing's going on. Okay, so then we start talking about the TCP IP version 4 protocol itself. When we talk about TCP IP version 4, the important thing to understand is that it is a protocol suite. It is numerous protocols that come together in order to give us this thing called IP version 4. We're looking at TCP, so Transmission Control Protocol. This is going to be the protocol that is used for the actual communication between the devices themselves. Once the devices have found each other, this is how they'll figure out things like session state, how much data to send, that type of deal. You have IP, which is the Internet Protocol. This is basically the addressing protocol. We talk about 192.168.1.1 with a Class C subnet mask. That is going to be your Internet Protocol. Under that, there's a whole bunch of different stuff out there. There's ICMP, Internet Control Message Protocol. This basically gives you the ping command. If you want to ping a computer, ICMP gives that to you. Now again, one of the things you have to be thinking about in the real world is sometimes 18-year-olds really, I don't know, they want to be James Bond or whatever. So they're like, I can ping the server. This is unacceptable. I'm going to shut off ICMP on the network. And you can do that, right? So again, if you're in a super secure facility, if you're in the NSA, God bless, turn off ICMP. Again, one of the things you have to think about is you have to worry about security, but you also have to worry about how you're going to manage and troubleshoot things. So if you turn off ICMP, it means you can't ping anything on the network, which means when you go and you do basic standard troubleshooting tasks, it is going to be an absolute and utter nightmare. So one of the things, you'll hear this, like everybody should turn off ICMP. Oh, please don't, unless you know what you're doing. Then there's another protocol called IGMP, Internet Group Management Protocol. It allows for things like broadcast communications. If you want to have one computer be able to broadcast communications to numerous other computers, that uses something called IGMP. Under this, I'm not quite sure where they actually fit in the protocol suite. You have things like FTP, other things. Again, these are different protocols, whether they're built on TCP IP or they're just with it, I don't know. But there's a whole bunch of different protocols there. So that's what we're talking about when we're talking about the protocol suite. So again, we're just going to say IPv4. That's what you say, but it is a whole suite of different protocols. Any questions on that? No? Okay, now we get to misery. Yay! We get to sucky time. Okay, so now let's talk about IP addresses. So anybody here who's a coder, you will know whenever people bring up regex, coders seem to groan for some reason. Regex is just miserable for code. It's actually not that bad. You look at regex, you're like, what are people complaining about? Well, basically, IP addressing is sysadmin's version of regex. Like, it's not really that difficult, but it just makes you want to cry. So we're talking about IP addresses. Again, we're going to have this. We're going to hear about this kind of thing, right? 192.168.1.1 with a subnet mask of 255.255.255.0, right? So this is what all these numbers are going to look like. And so the question is where the hell do these numbers come from? Basically, these are 4 octets. 1, 2, 3, 4, 1, 2, 3, 4. We talk about the octet, it's 1, 2, 3, 4, 5, 6, 7, 8. Basically with this, what you have, right? Yep. 1, 2, 4, 8, 16, 32, 64, 128, right? So these are the number signifiers for the digits in the octet. So if I do 1 here and 0, 0, 0, 0, 0, 0, 0, that equals 1. And that's how we get to 1, right? Let's see if I can do math really quick. So we want to get to 168. It'll be 1. That'll be too much. 0. That'd be 50, right? No, that'd be 60. 1, 0, 1, 0, 0, 0. So 168 is 1, 0, 1, 0, 1, 0, 0. That's how we get to 168. We say 255, that'd be 1, 1, 1, 1, 1, 1. That would be all 255. So when we're talking about octets and we're talking about the TCP IP numbering scheme, this is basically what we're talking about with those numbers. Now, why this becomes important is then we get to subnet masks. So when we look at an IP address, 192.168.1.1. When we're looking at this number, so has everybody seen a number more or less like this before? Right, okay. So when we're looking at this number actually has two identifiers in here. One part of this is the network identifier. The other part of this is the computer identifier. And so this is where we talk about LANs and we talk about WANs, right? So let's say we have a router here and we have a router here. They communicate with each other. So on this side, there's a whole bunch of computers, and on this side, there's a whole bunch of computers, right? So basically how you determine where the network part is and where the computer part is by the subnet mask. So 255.255.255.0. And so if you know what these numbers are, basically you may know, okay, all of the numbers up until here are used for the network. So therefore, that side is the network, that side is the computer, right? So if I have 192.168.1.1, that is going to be on the same network as 1.2, as 1.3, as 1.4, so on and so forth. But since that side is the network and this side is the computer, if this is 192.168.2.1, that will be on a different network. So that's where when we're connecting networks together, we will say something like 192.168.1.x. So that's my 1.x network. And down here will be 192.168.2.x network. And so basically, if you know it's that subnet mask, then that's the network, and these are the individual devices. Does that all make sense? Yep.
So by network, you mean like the cans and the gates?
It's a LAN, right? Yeah. So this is a LAN. That would be LAN 1. This would be LAN 2. And then if this is all in the same environment, this would be the WAN. Yeah. And then if it's spread over an entire city, that would be a MAN. Yep. Okay. All right. Everybody's nodding along. So I hate talking about this, so I will just pretend you all completely understand what's happening. So where we get to the subnet mask then, and where we get to those damn octets. Okay, so, all right, let's see, 192.168.1.1, right, with a 255.255.255.0 subnet mask, right? So again, these are 4 octets. 1, 2, 3, 4, 5, 6, 7, 8 dot. 1, 2, 3, 4, 5, 6, 7, 8 dot. 1, 2, 3, 4, 5, 6, 7, 8 dot. 1, 2, 3, 4, 5, 6, 7, 8. No dot, because that's the end. So anyways, if we look, so it'll be 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. What did I say? That's 128, so that'd be 1, 0, 1. So that's 128, that's 64, that's 32, that's 16, that's 8, 0, 0, 0. And 192 will be 1, 1, 0, 0, 0, 0, 0, 0. So this would be 192.168.1.1 set in the octets, right? And then we come down to the subnet mask. So 1, 2, 3, 4, 5, 6, 7, 8. dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8. So basically 255, right? So 255 is all of these numbers filled up. So 1, 2, 3, 4, 5, 6, 7, 8 is 255. 1, 2, 3, 4, 6, 7, 8 is 255. 1, 2, 3, 4, 5, 6, 7, 8 is 255. And then that's it, 0 the rest of the way. So basically, when we're looking at this is called a Class C slash 24 subnet. Basically, what happens is when you're looking at the subnet mask, where the ones end, right, that is where the network begins, and then everything on this side is going to be the computers. And so where this gets into the whole regex world is what will happen many times is, let's say for my network, right, I'm going to have a small network within the corporate network. So what will happen is my administrator will give me 192.168.1.1/24. So when we say /24, that's basically how many numbers are in the subnet mask. And so the thing is, what happens if I need multiple networks here? All right, so basically the idea is I only want certain computers to be able to communicate with each other. So I want the SQL servers on their network, I want the web servers on their network, and I want the few news users on their own network. So basically what would happen here is you look at it and you go, okay, so you kind of do it the other way around. So 1, 2, and you're like, well, I need let's say 3 networks. So I need 3 networks. So if I do this, it'd be 1 and 0 as a network, and 1, 1 as a network, and 0, 1 as a network. All right. So that's where I would take my /24, and I would say, okay, I'm going to turn that into a /26. And so now that side is going to be a network ID, and this side is going to be a computer ID. And that's basically where we're getting the mess. Again, God bless ChatGPT, you just ask them this question. You just say, this is my subnet mask, this is my IP address, I need 3 networks, and it'll give you the information. But basically, this is the idea here of when you start subnetting, basically the network that you were given, the subnet mask that you were given. When you then look at this, again, so you have 1, 2, 4, 8, and 16 here. So basically what this is going to be is you can have 3 networks on that side, and then 1, 3, 7, 15, is that right? 31? 31, and then it's -2. So then you can have, is that right? Maybe that's right. 1, 2, 4, 8, 16? Seems wrong, but maybe that's right. So basically what happens here is you get to a total number of 31. If you add these up together, you get to a total number of 31. The thing that's going to happen is on the low end, so basically on 0, what's going to happen is, I feel like I'm doing that wrong. Anyways, what 0 is going to be your network address. So again, the /26, that's going to be your network address, so you can't use that as a computer IP address. And on the high end, that is going to be what's called your broadcast address. So if any computer on that internal network basically sends out communication on that particular address, it will go to every single computer within that particular little network. And so this is basically what IP addressing looks like when you write out the octets. We all got to pretend you understand what that means, right? No, seriously, any questions? I do feel like I'm screwing up that number. I do hate octets. Anyways, any questions here? Nope. That is the right face to have. That is the right face to have. Again, a lot of this crap right here, a lot of this, you aren't going to have to worry about. The main thing to be thinking about is this. This is what you're going to get. And so when you see a 192.168.1.1 with a 255.255.255.0, basically what that's going to tell you in the programming world is that's your network, that's your computer. Right. Again, if you see /24, this is what you're going to see in the networking world a lot of times instead of the 255s, and that basically, again, tells you that, right? So 192.168.1.1, basically if it's a /8, that means that's the network, this is the computers. If it's /16, that's the network, that's computers. And if it's a /24, that's the network, and that's the computers. Again, hopefully you don't actually have to deal with this very often. The nice part, again, about IP addressing, again, the funny thing is when you get certifications, you have to learn all this stuff. And again, even me, I've been doing this stuff for 30 years. I have so rarely actually had to mess with any of this stuff in a production environment. Most of the time, people just give you the numbers and you plug the numbers in. As long as you have an idea of what's going on, you should be fine. Okay. We talk about A, B, and C. So again, there's always 5 different ways of saying the exact same word. So when we talk about a Class A subnet, that's 255.0.0.0. So a Class A subnet is this, or it's /8 is a Class A. A Class B is 255.255.0.0, or again, a /16. A Class C subnet, this is what you're almost always going to see, at least in home environments, is going to be 255.255.255.0. So that's the other way that you may hear about this stuff. Again, if you get confused, plug it into ChatGPT, they'll give you an answer. Again, see, I even put it in my notes. Scribble stuff on whiteboard. Impress students. That's really what you got to do sometimes. You're like, look, I swear I know what I'm talking about here. Okay. Then we talk about default gateways. What I give that guy crap about. So the interesting thing here, right? So you got all this octet stuff. There. So we have 192.168.1. Let's say 25. 255.255.255.0, right? So this computer, again, this is the network. So 192.168.1 is the network, 25 is the computer, right? So we have a router here, and this is one of those particular computers, right? Let's say down here, we have 192.168.4.105. Again, 255.255.255.0, right? We draw the line here. So this is the network, this is the network. So we have, our router here, we have the computers under the router, and this is one of those computers, right? So we understand how to identify the network, and we had to understand how to define the individual computer. But again, what is the real power of TCP/IP? Why do we care about TCP/IP in the first place? Is the ability to connect networks, right? The routability. So what's going to happen is on the internal side of this router, you're going to have an IP address. So 192.168.4, generally .1, right? And so this is what's going to be your default gateway. So 192.168.4.1, you'll have a configuration that'll show the default gateway. And so basically what is going to happen here is your computer down here is going to try to find this computer up here. I want to talk to 192.168.1.25. So the communication is going to go out in this internal network. It's going to say, hey, where's 192.168.1.25? Are you in the house? And there's going to be silence. It's going to be sad. He wants his buddy, right? It's like, crap, where's my buddy? Well, if you can't find his buddy on the internal network, it will then send that communication to your default gateway. That will then come to the router here. Again, we got router protocols, all kinds of stuff that'll be taught about in another class, and that will get sent up through the network to the other router, and that will come through here to be able to communicate with that particular computer, right? Again, this computer wants to communicate back. He's like, hey, I want to talk to 192.168.4.105. That communication will go out. It will fail because it's not on the internal network. So up here, it'll be 192.168.1.1, right? So this is the default gateway. So that communication will then go to the router, and the router will send it to where it's supposed to go, right? And this is where we talk about those routing protocols. Again, RIP, a whole bunch of different protocols out there. These routers are communicating with each other, basically to say what devices are on either side of them, so that when a communication comes in, they know how to route it throughout the network. And again, when I talk about that being complicated, that's where you hear about CCNAs, CCNPs, and CCIEs. Getting your CCIE will make you cry blood. Like, this stuff is very, very, very complicated. I'm very simplifying it here, but that's basically the idea. One of the things that you do have to be careful about when you're a new person, because this happens every once in a while, is you're like, okay, I set up my 192.168.1.2 network or whatever else. That's great. I want things to be secure. And so you're like, okay, and I'll set up this network down here. That's also 192.168.1. whatever. Like, this is a problem that happens in the real world. Well, you don't route to your same network, right? So basically, if this tries to do communication to 192.168.1.105, and this router knows this side is the .1 network, and it doesn't find it, it's not going to route to the other, because it's routing to a different network. That's what it's supposed to do. So if both networks have the same IP address scheme, the same network scheme, communication will fail out. So be careful with that. Does that explain default gateways? He smiles. John's like smiling, like, sure. Is this over yet? Okay. Then we get to private IP address blocks. So one of the big things when you get into the networking world is when you screw things up, things go catastrophically bad. There's something called Border Gateway Protocol. The only thing stupider than us using IPv4 in 2026 is Border Gateway Protocol being used. So the important thing on the internet, IPv4 was designed to be used in a trusted environment. So IPv4 originally was designed by the military. After the military, it got spread to the colleges. After the colleges, it went loose all over the world. The problem is it was supposed to be a robust system, but being used by known good actors. The issue is as the internet has expanded, we don't all agree with each other. I mean, there's a little disagreement between the United States and China, like weird shit happens. Anyways, and so like one of the things that you'll run into, like there's this thing called a Border Gateway Protocol, and one of the curious things that China has done every once in a while with this routing protocol is they will modify one of their configurations, and all of a sudden, if Joan is trying to send me an email, it will get routed through Beijing. Right? Because basically they modified a configuration. If people haven't hardened their configurations and their networking equipment, like literally, I mean, that's what can happen. Like literally, you can have an ISP in Beijing basically advertise a route. And if your ISP hasn't kept up with things, all your traffic is now going to Beijing for some reason. Like that's the kind of weird crap that can happen. And so again, when you're dealing with IP addresses, thankfully they were thinking about this back in the day, and they were like, how do we make sure that if users do something catastrophically stupid, it's not going to screw up the entire internet? And so that's where we have these private address ranges. So normally nowadays, again, as I showed you, 192.168, normally see 1, 2, whatever else, but you have the Class C 192.168 networks. That network, or 10.0.0 network, you'll see those a lot of times in ISP if you actually go into your modem or whatever. And then 172.16, I don't know, I used to see this like 20 years ago. You don't see this as much anymore. Basically, these are private, non-internet routable IP addresses. So even if somehow your computer is able to broadcast this IP address out onto the internet itself, the internet is just gonna not care. It's just not going to worry about it. So that's why we use this particular address scheme. So if you're looking at all this and looking at all these different numbers and you're like, why do I always use 192? Is because basically when you're doing internal networks, whether it's for your home office, whether it's for a corporation, it is almost always going to be one of these address schemes, just because, again, if it quote unquote leaks onto the internet, it's not going to cause anybody any problems. The private addresses make sense. Yep. Cool. Okay, then let's start getting to some equipment when we start talking about the network world. So crossover cables, hubs, and bridges. All right. Where do we talk about? So we're on page 9, in case you're keeping up. Switching ARP. Yeah. Okay. So the first way we did, we connected TCP IP networks together was hubs. First way you can technically do it is with a crossover cable. So basically you can have one computer, you can have two computers, and you can actually just connect them with a cable. There's something called a crossover cable. I've used one about 5 times in my entire career. I mean, they have a use, but you don't use them very often, right? Basically, the crossover cable just simply allows you to connect two computers together. You configure them for TCP IP with a subnet mask and everything else, and they just talk with each other and they're fine, right? That is what it is. Don't actually use it very often. But so you start thinking about, building these networks, and the first thing that they came up with was something called a hub, right? So you have all of your different computers, and they are connected to essentially, when you think of a hub, all this is like a cable splitter. Your house, you have a cable splitter, you put the connection in one side, you have 8 connections on the other side, and it splits. Basically the exact same thing for the network world. But remember, CSMA, CSMD. Hey, how do you think this is going to go? So remember, under the Ethernet standard, we have collision avoidance and collision detection. So basically, even with TCP IP, right, this person wants to communicate with this person. Communication goes into the hub. Again, it is simply a splitter, so the communication gets blasted out every single port on that hub. And again, back in the day, I actually saw 48 port hubs. So it could go out to 48 computers. 48 computers at once are connected by basically a cable splitter, right? So again, if 2 computers try to communicate at the exact same time, that comes in, there is a collision. That's where you get collision detection. They will wait a random amount of time before listening on the line again and trying to communicate. The issue that you run into, again, you got 48 computers connected to this one hub. You then daisy chain hubs together, because you really like your disasters to be big. And basically what happens is you have more and more computers. As they try to communicate, there will be more collisions. They will all wait a random amount of time, but you'll have so many computers trying to communicate at the same time, even those random numbers will be the same. So essentially, 2 more computers will try to communicate at the same time, and then you have a collision. And then 2 more computers will collision, and then more computers collision, then more computers in collision, and it all just goes to hell. And that is what we call a broadcast storm. Basically, all these computers are trying to communicate. Every time they try to communicate, there is a collision. They all wait for a period of time, but there's too many trying to communicate, so they all communicate again. Brah, disaster happens. That's a broadcast storm. That is why if you ever see a hub, if you ever go to school and they ask you what to do with a hub, it is trash can. You should have put it in the trash can back in 2000. Again, you want to talk about really bad education, why I get really frustrated with education. I had an employee of mine back in the day. He had signed a contract to one of these colleges to get his IT degree. He literally came in one day, and again, this was about 2009, and he showed me this networking diagram. It had routers and it had switches, it had access points, and then it had 2 hubs. I looked at him and said, quit your school now, get a refund. He was like, what do you mean? Again, it was 2009. I'm like, they're telling you to use hubs in a 2009 network. Like, they don't know what they're talking about. Anyways, so you get the broadcast storm. So basically the idea is, how do you deal with a lot of computers and a lot of hubs when you have broadcast storms? You do something called a bridge. So the bridge back in the day, what this did is it filtered MAC addresses. So when communications happened, basically those MAC addresses I showed you before, it has what is called a MAC address table in it. So again, all the different MAC addresses, it knows what MAC addresses are on this side, it knows what MAC addresses are on this side. Basically when communications hit this, if the MAC address is on the other side, it sends it through. If not, it stops it. So it tries to limit the whole broadcast storm scenario. And so that was the original concept with bridges. Any questions there? No, cool. So then we get to switches and we get to ARP, Address Resolution Protocol. And this is where we start getting into the IP addresses. And all this stuff actually does start to make more sense, I swear. So basically, again, even that thing with bridges, it's better than daisy chaining hubs, but not very much better. So the idea was a switch. Basically, what if we created a device that looked like a hub, but every single port on it essentially acted like a switch? So what happens is when you have computers connected to this, a computer will communicate the first time. The first time, communication will get broadcast out every single port. When the appropriate computer communicates back, then basically the MAC address of that computer is stored and associated with that particular port. So in the future, communication will go directly to that port and up to the computer. And then basically all these computers can communicate with each other and it's not interfering with anybody else. A big thing, again, if you go back 10 years ago, maybe 15 years ago, so anybody that has a legacy equipment, this can be an actual problem, is there something called the backplane. So whenever you look at switches, you'll see 10 100 switches. Nowadays, you'll see 10 100, 1000, so gigabit switches. You may have even faster switches. The important thing to understand with all of this is that is the port speed. That is the port speed. So 2 computers communicating with each other. But here's the thing to think about. You're going to have 20 computers concurrently communicating with each other. So it's not just the port speed, it is what is the overall, what was called, or what is called still the backplane speed. What is the overall speed that your switch can actually handle? And so that's one of the things when you go out there and you buy a $100 switch for Best Buy versus a $1,000 Cisco switch, one of the things you're paying for is actually paying for a good backplane there. So that's one of the things that comes up with switches. So basically then, what we get to is with TCP/IP is ARP, Address Resolution Protocol. So again, when we talk about the OSI model, there's 7 layers of the OSI model. Switches reside on layer 2, MAC addresses. TCP/IP resides on layer 3, again, the network layer, right? So basically you have the switch here and that contains the MAC addresses. But then you have your computer over here, and that cares about IP addresses, 192.168.1.4, let's say. So this computer wants to talk to 192.168.1.5. So it sends the communication to the switch, right? It gets broadcast out all the ports, and 192.168.1.5 returns an answer. But it actually returns 2 things. It returns that IP address, and it also returns its MAC address. Because remember, the switch cares about the MAC address. It doesn't really care about the IP address, right? And so basically, the communication comes back to your computer, and you have something called an ARP table. And the ARP table resolves IP addresses to the MAC address. So if I go to my computer right now, hopefully this won't take more than a second to run. Clear, so I can do ARP A. So this is going to show me, Jesus, okay, it's seeing a lot of computers. So this is the ARP resolution. So this is the IP address of some computer, I don't know, somewhere on the network that it's seen, and this is the MAC address. So when it's communicating with the switch, it cares about that MAC address. So that's basically how ARP and how these MAC addresses and things work with TCP/IP. So the important thing to understand is switch is at the MAC address level, routers are at the IP address level. Yep.
So if my computer wants to communicate with another computer, then would it send like the IP address or the MAC address?
So basically when it's trying to figure out, so if it doesn't have the MAC address in the table, again, how does this work? Anyways, I do believe when it doesn't have the MAC address in the table, it sends it out to the switch, and then that's when it gets the MAC address back from the other computer so it can actually fill out that ARP table. I think that's how that works. That's a good question. I will figure more about that. Again, this is all kinds of stuff. Just to be clear, you have to know enough about this to understand how it works. You very rarely actually get nailed for any of this stuff. It's just getting the idea of like, okay, so the MAC address table. Because that's the other thing with switches too. Again, we're in 2026. You shouldn't run into a problem with this, but just like backplane, again, 15 years ago, backplanes were an issue, there are MAC tables, MAC address tables within the switch itself. And you will see in the specifications, even now, especially if you buy a piece of Cisco equipment, it will tell you how big that MAC address table can be. And it'll say like 10,000, it'll give you a ridiculous number of MAC addresses. Again, if you're dealing with legacy equipment or cheap equipment, you might run into a problem with the switch actually has a small MAC address table for some reason. have seen that in the past. Okay. Then we get to, where are we at? I need to speed up. I just give you folks way too much information. I'll just keep on. Okay, so then we get to TCP. So TCP is what's called Transmission Control Protocol. So this is a protocol that is going to be basically doing the communication between the two devices. So the IP, IPv4, IPv6, that is what's going to connect the two computers together. Once the computers have actually found each other, TCP takes over to do the actual communication. An important thing to be thinking about in the security world is there's something called a three-way handshake. So basically the first computer, client sends synchronization packet to the server to initiate a session. Basically the first computer says, hey, I exist. The second computer then says, hey, I hear you. And the third computer then sends the acknowledgement to confirm and establishes the connection. This is called a three-way handshake. You will hear about hacking attacks. Basically, it's kind of like when you have somebody that's just being a real douche. Hey, hello, hi, hello, hi, hello, hi. Basically, that's when you can get what's called a SYN attack. Is basically when you set up a computer, the other person sets up a computer to never acknowledge the response. It just keeps saying hello as fast as it possibly can, and that basically tries to lock up a session. Again, that's something to be considering when you're creating your programs, when you're creating your software, is make sure communication properly happens. Another thing to be thinking about with TCP is something called windowing. Again, 2026, it still exists. You probably don't see it anymore. So anybody here remember 56K modems? This is the last time you would have actually physically seen. Jeez, holy shit. Wow, come on, Andre, you remember 56, okay, he remembers 56K modems, lordy. Anyways, this is something to be thinking about, again, with communication, with things, especially with real-time media protocols, when you're doing voice over IP, when you're doing communication, so TCP, all of this was built for a world 50 years ago. So basically what happens with windowing is you have the two computers, computer 1 and computer 2. So computer 1 will send a certain number of frames or packets basically to computer 2. Computer 2 will acknowledge the last one that was sent. This is the last one in order that was sent to me, right? As long as that matches what computer 1 thought should be sent, then computer 1 will send more data to computer 2. And then it'll send more data to computer 2. Basically, as long as computer 2 is properly acknowledging the last piece of data that was sent, this window will keep getting bigger and bigger and bigger and bigger and bigger, right? I don't know if you saw a movie where they used 56K modems. Basically what you used to see, right, you would connect to a file server, you would have a little progress bar here, and what would happen is you see bloop, 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 and then it would go like a long way, and then bloop, 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 go a long way, and then bloop, 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 right? And basically what was happening there is it's doing sending data, sending data, sending data. Okay, it's going good. Let me send you a big chunk of data. Oops, there was a failure. Okay, little data, little data. Ooh, lots of data. And basically that was happening. It kept trying to send more and more and more data until it hit a failure point, and then it would shrink the window again, more and more data until it hit a failure point, shrink, so on and so forth. Again, in a broadband world, in a fiber world, windowing still happens. It's still there. You probably are not going to see it. Where this might come into effect for you if you're using TCP IP, especially in IoT. So we talk about all these little devices spread all over the world, right? They might not be using a fiber connection. They might be using an LTE connection. They might be using a 3G connection, something like that. And so you might run into some weird communication issues. Again, this is one of the reasons too why voice over IP kind of sucks on TCP IP version 4. Because TCP IP version 4, right, was built for sending files. It was sent for images, that type of thing. It wasn't built for real-time communication. So if you send a big chunk of a text file, right, it doesn't matter. Right? Oh no, I got that big chunk of text file too fast, or that chunk too slow. Where you run into problems if you're doing voice over IP, that's where you can get some of that weird stuff, where you get kind of like a lot, or again, now it's 2026, but if you go back about 15 years ago, like you talk to somebody and then all of a sudden, like you get like a lot of words, and then it would be like silence, and you get like this, and this is basically what was happening. It was kind of doing this kind of thing. And so that's what we're talking about with windowing. And then finally, sessions. And so sessions, what we're talking about before, every communication between one computer and your server or the computer, that's considered a session. And so those sessions are set up with TCP. And so again, one of the big things to be thinking about is the concurrent number of sessions, especially with like computer software. Like if you use Windows, this is something you have to be careful about. So I don't know about now. I stopped using Windows a long time ago. Again, I used to be a fanboy. I hate it now with a passion. But like if you used a client operating system with Windows, many times they would limit how many concurrent connections you could have on the network. So I did this once. I had a client. They were pretty simple. They were big, but they were dirt simple. So I gave them a Windows XP box to be their file server, and it just did not hit me that they limited to 15 concurrent connections on the network because it was considered a client operating system instead of a server operating system. And so that's some of the stuff that you can worry about, again, with the TCP world. You then get the TCP ports. So again, TCP, Transmission Control Protocol, it's all about the communication between the two computers. So what the ports are, and again, anybody that's been in these other classes, you'll have seen this when we use the bottle example, is you have the IP address, 192.168.1.1, and then when you're using a web browser, you do colon, and for like bottle, it is 8080. So 8080 is the TCP port that bottle uses by default. And basically what you're thinking about with TCP ports is every service on your computer that uses the IP address basically will have its own TCP port for that service. Again, when you go do tests, SMTP, Simple Mail Transfer Protocol, is port 25. This is one of the things you'll see a lot nowadays with ISPs. ISPs got really annoyed with people having spam bots on their local networks. So a lot of times you'll go to try to send an email with SMTP and it will fail. And the reason is because your ISP has blocked port 25. Right? You have HTTP, so again, when you use a web browser generally, that is port 80 by default. HTTPS, we talk about things like SSL, that would be port 4043. FTP is port 20, and something called SSH is port 22. And so basically think about the IP address and the subnet mask. That is the address to get you to the building. The TCP port is going to be the actual suite number to get you, into whatever office, mail room, whatever, spa or whatever. The important thing to understand, again, especially when you're setting up servers, to be very careful, is you can't have two services using the exact same port, or everything is going to go to hell. The other thing is to make sure, and I've dealt with this in the real world, is make sure whatever you're installing has documentation worth a damn, especially if you're putting this into a secure environment. So my company used to install digital surveillance systems. I found a great digital surveillance system company with a very low cost with no documentation. The big problem that happened was users could communicate with the DVR from the outside world, but they didn't document what ports were used. And we found out it was like a port range of about 1,000 ports where it dynamically assigned the port whenever there was a connection. And it was a bit of a disaster for dealing with firewalls. So again, things to be thinking about. Let's see here, routers and default gateways. I think we pretty much explained those. Modems, when you deal with modems, basically what a modem is going to be whenever you use one. Again, you'll hear about a cable modem, a fiber optic modem, a DSL modem, a 5G modem now. Basically all modems are going to do is they are going to change the network communication from one standard to a different standard. That's all you're talking about when you're talking about with modems. Any questions? No, people are smiling, that's decent. Okay, now let's get to network address translation then. So that's what I was talking about before, basically with network address translation. What that is going to be is you have, again, your router, basically your modem for most of you folks. On the outside, it's going to have an IP address. Let's say 206.44.22.5. And then inside, right, inside, you're going to have a 192.168.1.x network, right? So all the computers inside are going to be 192.168.1. something, and then the internet is in the outside world. Basically what happens is when your communication goes out, you go to CNN.com, and basically the router tracks that communication so that when CNN.com responds, it goes to you. When one of your family members goes to Fox.com, they go out, it basically tracks that communication, and what comes back goes to them. And that's basically all we're talking about with network address translation. Where this gets a little bit interesting is something called port forwarding. And this can be one of those things you have to think about from an architectural standard, right? So again, whenever we talk about an IP address and we talk about a TCP port, there can only be one service on that TCP port. So when you're thinking about a computer, you can only have one service on a computer on that TCP port. But also something to consider is if you're going to have traffic that comes in from the outside world to your NAT-enabled router, that basically only one computer essentially inside that network will be able to accept that particular port traffic. And so that's what we're talking about with port forwarding. So we'll see here, right? So basically with this, the external port is port 80. You're going to go to 192.168.1.100. So this is where people talk about setting up a web server inside, their personal network. So I'm going to set up a web server in my house. So what happens is you point your DNS. So again, I have a DNS name of crappyapp.com. So what I would do is I would point crappyapp.com at the external IP address here. Whenever anybody comes in at port 80, again for the website, that would then get automatically routed to my web server. And that's what we're talking about when we're talking about port forwarding. The big thing to realize is if you have multiple web servers, then you have to figure out a whole bunch about configuration. So it's like, oh, I'm gonna have 3 web servers inside my premises. And it's like, well, if you do, I don't know. There's a lot of other stuff you can do, but basically the idea is each port gets forwarded to one IP address inside your network. That's the idea with port forwarding. Questions? Let's see. So yeah, so the internet-facing IP address. Again, if you want to know what your internet-facing IP address is, you can go to whatismyip.com. And so this is our external IP address here. So all this is reading, so you can set up very simple web app scripts on your own, and basically this will grab what the external IP address is. So outside this building, it's 136.41.224.92. So all the traffic goes out there and then comes back. Again, something to think about when we talk about privacy in the TCP IP world and how that's hilarious. Like, oh, that's adorable. This information is just sitting in a database. So literally, this IP address has information attached to it in a database. So simply by you going to a website, they're going to know that you're somewhere in this particular Raleigh area, you're using Google Fiber, and you have some of this information. So they can grab this information just from your IP address alone. But that'll be the external IP address if you're trying to figure out what that is. Okay, so then we get to firewalls. So if you're ever watching NCIS and they talk about they can't crack the firewall on the hard drive, that doesn't exist. It's encryption on the hard drive. Just use the right word. I was watching NCIS and they're like, the firewall on this hard drive. And I'm like, they don't have firewalls, damn it. Anyways, so all a firewall is basically it allows you to block particular TCP ports. So there's hardware and software firewalls. So you can buy a physical device that's a hardware firewall, especially if you're dealing with a corporate environment. It'll have a whole bunch of configurations in it. You can also have software firewalls. So in the operating system itself, if you've ever dealt with Windows firewall, you know that particular misery. Basically, all that does is it blocks particular ports. So it's basically going to say, I'm going to block any inbound ports on port 80. Why is that important? You're sitting there and you're like, well, I don't have a web server installed on my computer. Why am I going to block port 80? Because you got users, and they do wacky crap. They do just so much wacky crap. And so the thing is, if your user installs a piece of malware that then basically is a web server, right? That web server can be running on the system, when somebody tries to communicate it through it, let's say port 80, basically it will be blocked. So even though the server exists, it's blocked. The important one, more realistic, again, this is what we used to see in the old days, is somebody would put a email blast server. Basically, that would be the malware that would get installed in the system. And then all of a sudden, this person's computer was blasting out emails to everybody. Now you think about that, you're like, well, that sucks. That's not really that big a deal, right? Well, here's the problem, right? You used to have something called an exchange server. So exchange servers were email servers that were on your premises. So all the company's email would go through the exchange server, and then the exchange server would send email out through that external IP address. Well, here's the deal. If you have a bot on this particular computer and it's blasting everybody and their mother's mother emails, those people are going to start hitting the spam button, right? One of the things that gets tracked is that external IP address. So the ISPs and other vendors are then going to blacklist this IP address because of spam. Now, when the CEO goes to send out the payroll information so everybody gets paid on time, when it goes out, it will hit the blacklist filter and get bounced back and say you are a spam IP address and go pound sand. Again, I dealt with that with many customers, and getting them off of those blacklists is an utter pain in the butt. So that's one of the reasons to think about with these firewalls is even if the services are not installed on computers, you use that firewall to block the communication in case something does in fact get installed. When you do the firewalls, basically what happens is you can do inbound or outbound. This is another interesting thing. Be careful when you're setting up firewalls. They can really screw things up. So basically, if you block inbound traffic, what happens is any traffic that originates from the outside world will be blocked. But if your device communicates with the outside world and then a response is sent back, it will still function properly. The same is true with outbound. If you block outbound, then if inbound comes in, outbound should work. So basically, that's one of the things to kind of be thinking about when you set up these firewalls is figuring out the inbound rules, the outbound rules, the ports that you're going to use, all of this kind of stuff, right? Firewalls really come in to their own when you start building real infrastructure. The important thing to be thinking about whenever you design your systems is in the Windows world, there's something called global system administrators. They used to be. Basically, these have power to do anything on the network that they want. And what I always say is you should be able to put that username and password on a bulletin board, and it shouldn't matter. Your security should be so tight that even if a core principle of your security is violated, nobody can do anything about it, right? So if they have a global username and password, but they're not able to VPN into your network or whatever else, gain access to your network, then basically this information is worthless, right? That's the idea of creating a layered network. And so that's one thing to be considering, like when we start building systems. Again, you start building these AI systems. We talk about vector databases, we talk about other databases, we talk about data stores, that type of thing. What devices should these systems be communicating with? So somebody comes in and they talk to your web server, right? Well, you're gonna have a SQL server over here, and you're going to have, your what's called your SAN, storage area network over here, and you're going to have other servers around, right? So one of the things to consider is you can put firewalls up. So basically, the SQL server can only communicate with your web server. Don't quote me, I think I put it in there, port 3306. I think that's the MySQL port, right? So basically, you can say, okay, we will allow inbound traffic from this particular server on this particular port, and we will respond to it. If a hacker is able to infiltrate my network and tries to communicate with a SQL server, it'll fail. Even if they have the username, even if they have the password, even if they have everything, it doesn't matter because the firewall will block the communication unless it comes from the specific computer. And this is the kind of thing to be thinking about with these firewall rules, all right? Again, a lot of the stuff that's going on with cybersecurity right now, I lose my mind. A lot of administrators need to go to jail. No, and like I say that, and people laugh because they always get a little nervous when I say it. But so many of the cyber attacks that are currently happening, it is gross negligence. The thought that it's somebody making hundreds of thousands, don't get me wrong, if it's an intern, if the intern was responsible for the email server and the email server fails, okay, pat them on the head, send them home, give them a chocolate chip cookie. But if you're paying a CIO, CTO $250 a year, and again, and they have a budget that is worth a damn, when you look at these attacks against hospitals and other institutions, it is literally gross negligence in 2026. In 2006, it was bad policies and bad decisions. At this point in time, we know how to secure all this stuff. Anyways, okay. Then we get to DNS. Page 13. So basically what we're talking about with DNS is we're talking about IP addresses, right? So IP addresses is what our computers care about. So again, we talk about TCP IP version 4, everything is going to be an IP address. But you're not going to remember that. It's like, oh yeah, I want to go to 205.66.54.1. Did you see the meme on 211.66.4.5? That was hilarious today, wasn't it? Like, no. You want to go to Reddit. You want to go to Reddit, right? So basically, when we talk about DNS, all DNS is called domain name service, and what it does is it resolves what are called fully qualified domain names to IP addresses. So if you are on a local network, you'll have what is called a host name. So you may have server or Jupiter or whatever the hell your naming convention is, and basically that is going to resolve to a local IP address. If you're going out to a web server, cnn.com, crappy-app.com, basically it's going to point to an external IP address, and that is all DNS is. All DNS is resolving fully qualified domain names to IP addresses. Essentially what happens is a resolution order, and you do have to be careful about this. Oops, I have to be careful about spell check. Anyways, so the first thing they're gonna hit is your DNS cache, So you go out to DNS, you modify the DNS settings, you go to your computer, you try to go to the website, and it fails miserably. And you're like, because you screwed up the settings. Nope. First thing you need to do is you need to flush your DNS cache, because it's probably just saved in that cache, and that's what you're resolving to. After that, you have something called a hosts file on your computer. Host? That should be host. Host was LM. Anyways, there's a host file on your computer. So this is actually a text file on your computer that basically has the IP address and it has the domain name. And so the computer will look at that to figure out basically where it should get routed to. This was the hacking attack that was done, again, seems so weird to say all this, 20 years ago. Spyware or malware would get onto your computer. You would try to go to CNN.com and then you wind up on sextoys.com for some reason. You're like, what the hell's happening? Basically what happened was the malware would get on your computer, it would rewrite your host file, and so every time you try to go to CNN, Taco Bell, whatever else, it would route you to wherever they wanted you to go. Anyways, then after that, you're gonna have your local DNS. This is either gonna be your small office, home office, router modem, basically that little router modem you've got, or it'll be something like a Windows server or a Pi-hole. So this is going to be the local DNS. This is where the hosts are gonna be. So again, server is going to point to 192.168.1.10. Print server is going to point to 168.1.25, whatever else. That will be on the local DNS. And then you'll have your remote DNS. Those will either be your ISP, Cloudflare, Google. They're called recursive DNS resolvers. And that is where the CNN.com, that kind of thing is basically going to be stored. That is the very basic idea of what's going to happen with DNS. Any question there? No. Then you get to reverse DNS. So again, especially if you're in the Microsoft world, Microsoft is actually pretty good, especially in the corporate environment. So one of the issues you run into, again, with that whole, like the host file, is what happens if, essentially if you have a spoofing attack. Basically, you're trying to go to TacoBell.com and they keep going to sextoys.com, runs into a problem. So basically, DNS resolves a fully qualified domain name to an IP address. What reverse DNS does is it resolves the IP address to a fully qualified domain name. So basically what's going to happen, you're going to go to TacoBell.com, you're going to get returned an IP address, then your reverse DNS server is going to take that IP address and see if it matches TacoBell.com. If it matches TacoBell.com, you're going to be able to go through. If it doesn't match TacoBell.com, generally the communication will die. So that's the essential idea of what a reverse DNS server is. Questions? Nope. Okay. Then we get to GeoDNS. Really do need to fix my things. Anyways, so basically with GeoDNS, this is what I talked about before. Again, this is something you have to be thinking about with your architecture. And does it matter? FTP servers are not going to matter. Voice telephone agents will probably matter. And so all GeoDNS is basically when a user resolves to the DNS server, based off of where they are located, they will get a particular IP address back so that they can go to a particular server. When you take a look at this, again, if you're interested in doing this, plug in GeoDNS and then see all of the ads pop up. There's a whole bunch of different names for GeoDNS, so it might be different things, but that is basically what's going on. Again, the idea is that somebody in India will be sent to an India server, somebody in the United States will be sent to a US server, and this will all be done using IP addresses, not using anything else. And sorry, 1 minute, somebody's left, so I do have to make sure I get a picture of all you pretty people. Pictures? It's not on the internet, it's not real. Okay, so that's basically what's going on with GeoDNS, and it can be incredibly useful. Again, especially when you start thinking about like this AI stuff. You know, one of the things I consider nowadays, it doesn't get talked a lot about, but one of the problems with a lot of these new LLMs is they're getting trained on everything. And the problem is, like anybody else, if you get trained on everything, you're probably bad at a lot of stuff. So what was really curious is the South Koreans actually came up with their own model that only knows Korean, right? And again, you say something to it in English and has no idea what the hell to do with it. But the idea was if it's only trained on Korean, it's going to be a hell of a lot better at dealing with Korean than, you know, OpenAI is going to be. And so again, that's one of the things to be thinking about too with this whole AI world when you route people is again, things like language. Like if you have something that is specifically trained only on one person's language, that might be better than all of these different languages, that type of stuff. Also, again, with GeoDNS, we have all this stuff going on between the US and China right now. Again, China is coming out with some great models, and we're told not to use them because they stink. China man stink. You wouldn't use a stinky model now, would you? No, use an American model. Anyways, this stuff is gonna get weird. This stuff is gonna get so stupid so quick. Again, just to understand, I try to stay out of politics, especially in classes. In classes I do. If you want to understand complete and utter stupidity, so the Biden administration, they were putting through these export controls, and so they wanted to control GPUs, hardware, right? China should not be able to buy hardware. And so that is what it is. Like maybe it's good, probably not, but it is what it is. They literally put on the table, I crap you not, they were going to put export controls on open source models. If you helped a Chinese researcher build an open source model, it was going to be a felony. Like, this is not a joke. So when we talk about how stupid this is it's gonna get so stupid. It's gonna be just stupid upon stupid. So anyways, so things to be, and again, something to be thinking about, like with the Trump administration now, again, not with the politics, you'll notice how chaotic it is, for a polite word. Again, think about this. If you are the decision maker in your organization, it is your job to think about what happens if the world goes bat crap. Just like it's your job that if, you know, what happens if there's a biblical flood, your system should be able to handle it. What happens if there's a biblical executive order? Again, this is something to really be considering right now and planning for. Because again, like there's a whole bunch of stuff like, well, in 3 years, when this guy's out of office, the next person will get in. But again, it's amazing how many policies Biden kept from the first administration, from the first Trump administration. So again, things to, when I talk about this, stuff to be thinking about. So we get to SSL. This is something in the TCP IP world. So we talk about encryption. So encryption is a big deal. You'll hear about encryption at rest and encryption in transit. So encryption at rest is when you encrypt your hard drive, which may or may not be a good idea. Remember, when you encrypt your hard drive, it means hackers will not be able to compromise your hard drive. It also means when your operating system fails, I will not be able to recover your data. So think about what security actually means. But anyways, basically with SSL, this is a big thing on the internet now. Basically communications between two computers are supposed to be encrypted using SSL communication. This has been pushed really hard. The issue that you run into at this point in time is setting up SSL can be a little bit of a pain in the butt. You know, it's not too bad. There's something called Let's Encrypt. You can do it for free. It'll take me about 2 hours to teach you how to do it. So it is a little bit of a learning curve. You can buy certificates from companies like GoDaddy or whatever else. You can install those. They'll take you about an hour to figure out how to do. One of the things that I tell people nowadays, though, is Cloudflare DNS for SSL is absolutely fabulous. So basically what happens is you buy your domain name from Cloudflare, you do like 3 configurations, and then SSL is working. So like we had the Twilio example, the Twilio class a couple of weeks ago. Part of that, they have webhooks, so you can actually have their agent communicate with your bottle server. The problem is it has to be SSL. You can't do it plain text. And so all I did was I did crappy-app.com, basically bought that through Cloudflare, turned on their little SSL thing, and I have SSL. I don't have to install certificates. I don't have to buy certificates. It all just kind of works. So that's one of the reasons I recommend SSL, at least for lab environments and that type of deal. That's basically what we're talking about with SSL. Any questions? Nope. Okay, we get to DHCP. Where are we at? Ugh. Okay, then we get to DHCP. So when you're setting up your IP address scheme on your premises, the issue that you're going to run into is the same issue that the ISPs run into, is that you're only going to have so many IP addresses. Again, when we talk about 192.168.1.x, basically this is going to give us 254 IP addresses in total. Basically, and that is going to have to be for everything. So that is going to be for your server, that is going to be for your router, that's going to be for all your Wi-Fi access points, that's going to be for your print server, that's going to be for everything, right? So imagine you have an environment, again, especially something like a cafe, a cyber cafe. You're going to have people coming in, they're going to be using the Wi-Fi, they're going to be leaving. So you can assign or set up static IP addresses. People hard code their IP addresses in, but if they do that, they're going to screw it up. It's going to be a disaster. So what you have is something called DHCP, Dynamic Host Configuration Protocol. And basically what this is you're going to have what's called a DHCP server. In that server, you're going to create a scope. So you're going to say, these are the IP addresses you are able to basically lease out to anybody that connects to the network. And then when somebody connects to the network, they will then be given one of those DHCP addresses. When DHCP gives them the address, they will be given the DNS servers. So whatever DNS servers they should use, that will be part of DHCP. And the default gateway will be presented as part of DHCP2. So basically, they can simply connect to the network. They get all of this information, and they should be able to do whatever they need on the network. And that's basically the idea with DHCP. When you have the DHCP servers, this is probably going to be built into your little modem router thing that you have in your home. Do be careful in the Windows world. Windows gets really weird when people set up their own DHCP servers. So basically, Windows and DNS, Windows DHCP and DNS are tightly integrated. Again, Microsoft likes to tightly integrate things. Works wonderfully when it works. If you spin up your own DHCP server, or basically not spin up, if somebody plugs in a Linksys router onto your network and isn't thinking about things, Windows doesn't like 2 DHCP servers running at the exact same time. And sometimes it will, for some reason, shut down its own DHCP server and just let the other one give out addresses, which can be its own disaster. So anyway, something to think about with DHCP. So basically with DHCP, you have the scope. What then happens is it leases out the IP address for an amount of time. This is something you have to be thinking about. So if you have a static environment, everybody comes into work, they have a desktop computer, you will still use DHCP, but you may have that lease at like a week. Remember, anytime a computer does something, this requires resources. So you just set it for a long period of time because it's not going to matter. The environment is not going to change very often. If you were going to be doing like a Wi-Fi cafe, then you might shrink that lease down to about 12 hours or a shorter amount of time, basically so that the DHCP server knows to basically kill that lease. What will happen is essentially, depending on the configurations of the DHCP, what's supposed to happen with a client computer is about at the halfway mark. So let's say you have it for a week. At about 3.5 days, it's supposed to re-request the IP address. If it doesn't get a new IP address or doesn't get that renewed, and half from that it will re-request, half from that it will re-request, half from that it will re-request. And this is one of the times you can have really weird problems when like the DHCP server crashes at some point. But again, I talk about hard fails and soft fails. This is where you can start having a lot of weird soft fails all over your network. because all of a sudden, randomly, computers stop working on your network and you can't figure out what's going on, because the network seems to be working. And the reason is because their DHCP leases start to fail, and you don't realize that the DHCP server failed like a couple of days ago. Something that can happen. So that's there. Yep. Then you have VPNs. VPNs, be very careful with VPNs right now. Everybody knows about CloudBot. Everybody knows about that disaster. OpenClaw, you know OpenClaw? Come on, you know OpenClaw, no? Okay. OpenClaw is basically how to speed run destroying your infrastructure. So basically what you have with OpenClaw is you can install this AI agent onto your computer. You give it root access to your computer, and I don't know how this is not supposed to be a disaster, right? Anyways, one of the things to think about with these agents, so we talk about spear phishing attacks. When we talk about cybersecurity or spear phishing attacks, the big problem with things like spear phishing attacks is when somebody sends you a link and you click on the link, the real fundamental issue, again, we talk about layer security for cybersecurity, is that little executable will fire off with the privileges of the current user that is logged in. So if you're a smart systems administrator and you have a crappy ass user account with no privileges, when you get hit with that spear phishing attack, it's probably not going to do a damn thing because you don't have any rights to do anything, right? Your account, like you may be the CIO of the company, but your account doesn't have the ability to add a printer, right? What gets really concerning right now is we have a lot of these coders out there who are literally putting OpenClaw onto their computers and running it at their privilege level. So if they're administrators on their computers, they're running it at that privilege level. Think about this for a second. So what do we got with VPNs? So VPNs are a little bit old school, but they still exist. So let's say you are a salesperson or a remote worker, right? And let's say you have internal file servers in your company or print servers in your company. Basically, you're out in the normal world, but you need to access these local resources. Basically, what a VPN does, it's called a virtual private network, is the first thing that happens is you create a tunnel through the cloud. There's this tunneling protocol that's created through the cloud. And basically what this does is it tries to detect if anybody is trying to compromise the tunnel. So you hear about something called a man-in-the-middle attack, basically where people are trying to read communication. So basically this tunneling protocol will try to see if that's happening. If it detects that's happening, it will drop that connection. And as I said with the internet, it will try to reroute it, right? The idea is basically to try to go around that man-in-the-middle attack. And then inside this, they now use SSL. They used to use a different encryption standard, but it's SSL communication. And so this traffic is encrypted. So the idea being is even if a hacker is able to compromise a little bit of your communication stream, even what they get is still going to be encrypted. So the idea is they grab that, the tunnel drops. Even when they go to analyze the information, they're not going to know what to do with it because it's encrypted. But here's the issue. You install OpenClaw on your computer. You are a global administrator because you want to go to jail. You want to prove Eli is right and go to jail. Global administrators, again, in the Windows world, have access to do anything they want on an Active Directory network. When you access that VPN, it is logically as if you're on that internal network. You see all the AD servers, you see all the print servers, you see all the file servers, you see all of the servers. You now have your OpenClaw agent doing whatever the hell it's going to do in there, right? So this is going to be one of the big problems, again, with OpenClaw and stuff with VPN, is understand when somebody connects and they're running this, they're going to be running at the privilege level of whatever they're logged in as. And so when they access your internal network, they are going to be running at that privilege level too. And it's amazing. Like I hear so many of these tech professionals, and again, they're not, it's called sandboxing. Sandboxing is when you put this stuff into its own little world and you make sure it can't talk to anything it's not supposed to. Like so many of these people are installing this crap directly on their system. And the other thing to be thinking about too, if you don't think about security properly, especially with Active Directory, is have you ever dealt with salespeople? You want to lose your damn mind in about a fucking heartbeat? Because here's the problem with salespeople. Salespeople bring your company lots of money, right? The entire reason you have a big-time salesperson is they bring your company millions and millions and millions of dollars in revenue every year. And the thing is, when you bring a company millions of dollars of revenue a year, you get to do whatever the fuck you want to do, right? And I've dealt with this crap in the past, where you go to the big boss and you're like, look, I can't stop them with my systems. You need to discipline your employee so this crap stops. And I've had an executive director go, do you know how much that guy is worth? I'm like, I don't care. And they're, right? And so that's gonna be one of the big issues. Is again, it's not even the IT, like the developers or whatever, but everybody. And that's why I talk about the AI, where I get really concerned with AI, is every normie wants to get on this bandwagon. And what happens when they're VPNing with this kind of stuff? And this is the kind of stuff that you need to be thinking about in this AI world. So that's basically what the VPN is, and it's why you should be scared. Scared, 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 scared. So scared. And again, this is the kind of thing we need to be thinking about when we talk about artificial intelligence, is again, how do you start defending against these attacks? I went to an All Things Open meetup a couple of months ago. So All Things Open, if you don't know, definitely go to All Things Open meetups. But it was interesting because the guy was talking about using these coding agents, and that's when he showed me this whole list of privileges that his coding agent had. So I just raised my hand. I'm like, yeah, so what's like the Active Directory equivalent, for AI? So Active Directory, this is security, so locking off the ability to change things on computers, locking off the, so I was like, what's the act? And literally this guy sat in front of like 150 people, he's like, well, you trust your developers, don't you? I was like, no. A, I don't trust them, and B, I sure crap don't trust this stuff. But again, like what's interesting right now is so many professionals really aren't thinking about, again, think about this stuff at scale. Okay, getting close to the end. So one of the final things is proxy servers. So you're gonna hear about proxy servers a lot. Again, NAT versus proxy. Ask your grandma. So how do you feel about the NAT versus proxy situation? I'm like, what? Anyways, so basically all a proxy server is, this can be useful for you in your environment. So basically you got all of your computers, right? They're going out, they're going to the internet. So before NAT existed, you may have heard of WinProxy. I don't know if anybody else heard of WinProxy. Anyways, we used to have these things called proxy servers. You still have proxy servers called Squid. If you have not played with Squid, I would highly recommend you play with Squid. It's a cool little tool. Basically, this is a server, and what it does is it shares an internet connection for all of your users on the network. The cool thing about proxy servers, especially in things like the AI world and for security and all that, is basically it can log everything within that proxy server, and it can also do caching. So again, caching can be very nice. So back when I had my computer repair company, one of the things that we did is we had a Squid caching proxy server. So when we needed to install service packs on Windows computers, right, the first computer would go out to Windows and download the entire service pack. The cool part was that service pack got cached inside our Squid proxy server, so the next user that wanted the same service pack, they were able to pull it from the local network instead of going all the way up to the internet. So again, that's basically the idea with proxy servers and something you might think about. Reverse proxy servers is probably going to be more significant from an architecture standpoint. And basically reverse proxy servers are that in reverse. So users are coming from the outside world. They then hit what's called a reverse proxy server. So we do these examples with Bottle. So Nginx is what's called a reverse proxy server. So we use it to a very small degree for our projects here. But the idea is you can have multiple servers running. And then what happens is the reverse proxy server will route the user to the appropriate server based on any number of particular circumstances, right? So it's like you could have, let's say, one of your web servers is using a GPT OSS. So this is OpenAI's model, so it requires a decent amount of resources. So let's say you want to give your users the best possible option, so you'd go do GPT OSS. Then let's say maybe if too many people are hitting that, so that's getting overloaded, maybe you have a different server and you're using Granite 4. Again, my favorite, let's say you're using a 3 billion parameter model, so you can use that on a bit crappier server. So your users are still getting a response, maybe it's not as good. And then the problem is if that server gets overloaded and those server gets overloaded, you're like, crap, again, we do want overflow. We don't want to have to pay. So this is a single fixed cost, right? This is a single fixed cost. But if we're getting too much traffic in, maybe this server will do an API call to OpenAI's API. So they have an API, you get charged $1.50 per million tokens. So basically, if these computers are getting overloaded, maybe it gets routed to that one at the end of the day. And basically, the idea with that reverse proxy server is it is then sending traffic to the appropriate. So you may have like a cluster of web servers. Again, you're doing load balancing over those servers, and maybe for different purposes, that type of deal. That's basically what we're talking about with the reverse proxy server. Yeah. That's basically it. There's a few more examples, a few examples here of different commands. So if you go use the ping command, let's see if you see this. For anybody that needs to know this, Control C. If you do ping 1C, c1cnn.com. Well, let me do that. Clear. Come on. So ping c1cnn.com. So why I do this count one, so if you're on Windows, it should ping 4 times and just give you the results. If you're on Mac or if you're on Linux, when you do ping, it will keep going until you manually stop it. So you give it that count 1. Basically, when we get this result back, this is going to give us some information to take a look at. So it's going to give us the IP address that we're resolving to. So this can be valuable, especially if you got quirks. Again, if you want to script this out a little bit. So when you start dealing with large companies, especially software as a service, like Salesforce has like 10 or 20 IP addresses it will direct you to. So you want to talk about a miserable soft fail is when one of those IP addresses is failing. So you have 20 people in the company that use Salesforce, and 2 of them, Salesforce isn't working properly. Why? Because when they resolve whatever IP address they're resolving to, that server is down. Whatever IP address everybody else is resolving to, that server is up. And so you're like, the network's up, the sessions are working, why? So anyways, that can be one of the problems. The other thing here is it will give you your latency. Again, CNN.com, that's very impressive for a news site. So you have 11 millisecond latency there, right? So if you're going to websites, that's fine. But again, if you're like trying to figure out like why the voice over IP server isn't working properly, you ping the voice over IP server, you see that your latency is up at like 300 milliseconds, then you know what the problem is, that kind of thing. Basically, that's the kind of thing there. Again, if you ping something and it's not up, it will give you a fail. So that's ping. What else do we got here? We have traceroute. Let's see if this works for. Basically, what traceroute is, it can be useful if you actually own all of your network. I don't think it's going to work for. Let's see if it works for this. EliTheComputerGuy.com. So basically what this is going to do is this is going to give you a response from all the hops that it takes to complete the communication to whatever device you're trying to communicate with. So this does require ICMP. Again, when I talk about ICMP, so we go through 10.255.255.254. That hit with 2.83 milliseconds. So that's probably the ISP's IP address there. And then it kind of depends on like what kind of ISP you have, how much information you get here. Sometimes you get more or less information. It looks like we're going to get a lot less information with this. But like if you own your own network and you're going through multiple layers of a network, you should be getting responses from all of those different layers in the network. Yeah, this is failing out for a lot of stuff. Let me see. What if I do trace route silicondojo.com? Yeah, same address. Yeah, let me do one. Anyways, trace route. We're not going to get a great response from there. We do have an example in the book. If you look at page 17, that will give you a pretty example when I pinged silicondojo.com from home. I showed you the ARP. So the ARP address, again, the ARP, that gives you all all of the IP addresses to MAC addresses. Basically, that gives you that information. So this can be useful when trying to figure out the different devices on your network, if you're trying to map your network and figure out what's going on there. ARPA can be useful. And there's a whole bunch of these kind of tools. So again, you go in the TCP IP world, and you can start playing around with this kind of stuff. When we get to AI, I have an example here. So we go to page 18. We have labs. So you can play with these labs at home. Let me see. So basically the idea here is that we're able to ask questions. I don't know how well you can see that. Ask questions from an ARP dump. So I do think this is one of the interesting things with the AI world. Like everybody wants AI to do the work for you, which I think is a bad idea. Maybe in 2036 it'll be good. Right now, a little questionable. But one of the nice things is I kind of think about AI as like, what if it's like a spell check for your career? Again, you just like dump information, be like, what did I miss? Right? And it gives you information back for you to deal with. So basically what happens with this particular little script here, so this is just a Python script. We're using Ollama, which is a standard, so this is, Ollama is the LLM framework we use for most of our classes. Basically what we do is we use the OS module. When you use os.popen, so the popen function, what this is going to do is this is going to fire a command on the command line, and it's then going to return the response into this variable value. So basically this is going to come back as an object. We are going to read the object, and that value is going to go to network. Then what we can do is we're going to just print out the network so we see what it is. It's going to be very long for here. And then we can ask questions about what is in this particular dump, essentially. We use GPT-OSS. Again, GPT-OSS is OpenAI's model, so it's actually pretty good as long as you've got a decent computer, and we can ask questions. Again, this ARP dump is going to be bigger than I was expecting, but we'll see what goes on here. So I can run this. It's now doing the ARP dump. ARP dump, ARP dump, ARP dump. There we go. So basically that is printing out everything. So these are all the computers that it sees on the network. Now again, the cool thing with AI, and again, remember it's pattern recognition, I can do things like list all of the vendors of computers you can recognize from these MAC addresses. So this is GPT-OSS. So this is a M2 Max MacBook Pro from about 2.5 years ago. So this is about the speed this works on it. Bum 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 ba dun da dun. What's that? GPT-OSS. So this is OpenAI's open source model. Yep. 15, 16? It's the big one. It's a big one. Yeah, yeah. As it's doing it, we'll answer that question for you. Yep. Oh, Lordy. Yep. Ollama, GPT, OSS. It is open weights. So, I guess this is the 20 billion parameter model. Yep. Yeah, I didn't realize it was that big. Yep, so it's 20 billion. Yeah, 14 gigs. Yep. And again, this is the kind of thing you need to be thinking about when you're designing your systems about response time. So again, in all seriousness, again, this is like a $3,000 computer. Like, oh, I've got to buy a $40,000 GPU. But imagine if this is just a script going on in the background. So imagine this just script is going 24/7 a day doing whatever, and then you can just get a report at some point or an email or whatever else. Come on now. Come on. Tap and dance, tap and dance, tap and tap, tap, tap and dance. Oh, there we go. So let's see here. Oh wow, yeah. So it spit out a lot of stuff here. Kind of ugly. Kind of ugly. Vendor Apple Inc. So it says the majority of the MAC addresses in your list belong to Apple hardware. Mellanox Technologies. The overlap. Many of the same prefixes are also used by Mellanox. The overlap means those machines could be either Apple devices or Mellanox. Cisco, shows Cisco, Dell computers, HP computers, Netgear, D-Link, Samsung, Huawei Technologies. A couple of addresses correspond to Huawei and ZTE, right? So again, if you're doing, like, this is the kind of thing to think of, like, again, there's gross negligence. A lot of people need to go to jail, just to be clear. But there's also just, again, auditing your network, especially a large network, is genuinely difficult. And remember, especially if you've got active ports, anybody can plug things into those active ports and you have no idea what's going on. So one of the things to think about is you could have this AI thing just scanning through, and then I look at this, and again, like, what's surprising to me, like, oh, why the hell is there Huawei equipment on our network? I should probably look into that, right? So that's the kind of thing. And again, if it did not take so long, I would ask numerous questions, but we don't want to go through that too long. Yep.
A lot of end user devices, like in the last 3 years, the Macs, mobile phones, Windows, they rotate the Mac address, so they just randomize it as part of the setting. So that's why the Mac throws off sometimes.
Okay.
Cisco, the router, the net, that will be correct most of the time.
Yeah.
But for end user devices, the MAC address is just randomized, rotated every time you connect. So that's why I was saying it's not unique anymore.
Yeah, okay. I'll look into that. It used to be completely unique. We'll look into that. Yeah, is that, yeah. What's that? Yeah. So anyways, so that kind of thing is there. So that's that particular example. Again, think about like dealing with the ARP. And then the other thing you can do is this ping. So basically the idea we have here, again, imagine this is, you want to make sure what's going on with your network, why there might be any problems. So basically what I have here is I have a list of domains, fully qualified domains to ping. So CNN.com, Fox.com, TacoBell.com. And basically what happens is we do for site in host. So we do a loop. We ping each one of those sites. Basically, we add that to the list, and then we can feed that to the AI to ask questions. And so, like when I run this, it will tell me things. Like, so I can say, so we put Taco Bell in there. Oh, see ya. So we put Taco Bell in there. I can say, why am I having problems with TacoBell.com? Dun, 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 dun. Swear it was working faster at home. I guess I have to buy one of those new Macs now. Anyways, there we go. So we go, we take a look. Yeah. Got a lot of information. Okay. So ping TacoBell.com is resolving to 127.0.0.1, right? So basically what happened is a long time ago, I was doing a test, playing around. I built a little website on my computer, used the host file, pointed Taco Bell to 127.0.0.1. So now whenever I try to go to Taco Bell, it fails out. So again, this is a simple way, like you're dumping essentially that kind of dynamic log file, and they're able to ask questions about, what's going on with it, right? And so again, that can be just an easy thing, right? You dump the file and you just say, hey, why am I having this particular problem? And it might be able to tell you, what's going on. Let's see here. I can say like, how are the sites doing? I don't know. Let's see what it'll do. Probably get better with your requests. But again, let's say you had like a list of 20 different sites that you're going to, or 20 different IP. Remember, it gives you that latency. So it might be able to pull out like, oh, the latency for this particular site is higher than you thought. So let's see here. Yeah, again, GPT OSS gives you a lot of information. So yeah, it fails out for TacoBell.com. Then it says, you know, what does a ping CNN, tells me packet lost, the latency, that type of thing. Again, my latency for Taco Bell is 0.09 milliseconds because it's on the same computer. So it says no packet lost, all 3 hosts reply, low latency, bottom line, right? CNN and Fox are reachable and performing normally. Taco Bell is resolving to your own loopback interface. Right, so again, you can do that kind of thing. And so yeah, that basically kind of gives you an idea of how you can start using AI with some of this TCP IP stuff. And then just in general, when you start building your AI systems, why TCP IP matters. So that is the class. Any questions on the class? Yes.
So going back to like GANs, would you consider Starlink a GAN then? Even though it's at like a carrier level?
So that would be internet.
Yeah.
So,
But technically your access points, right?
well, no. So the GAN would be Starlink's backend.
Yeah.
So whatever Elon Musk is using to manage all those satellites would be the GAN. The service that you're accessing would be the internet. You know what I'm saying?
Yeah, I'm like satellites inward, but without talking to the internet yet.
Yeah.
Since satellites are basically your access points, right?
Yeah. So it's like, yeah. So you'd have his ground stations and his other things communicating with the back end of the satellites. And so yeah, again, it's all logical. It's a way of thinking about it more than anything else. But yeah, that part would be the GAN. When you put out your little dish and get the internet, that would be the internet. Yeah.
Yeah, back to network address translation. So you mentioned that like 2 hosts, you know, they can't use the same port on the same network. So
Yep.
like if you had 2 web servers on the same network, and say they're both using port, I don't know, 4,000. I don't know if
Yeah.
it's valid port. But I mean, how would you be able to serve clients that are trying to pull like either web server? Like, is there?
So basically you would use service, haven't used it in years. There's a service called noip.com. noip.com. And one of the things they can do is something called port 80, here, I'll just do this, port 80 redirect. So basically what a port 80 redirect does is it redirects port 80 traffic to a different port. So basically, so you would use like noip.com as your DNS provider instead of something like Cloudflare. So when somebody goes to crappyapp.com, the default is port 80. So what noip would do is it would resolve, but then it would switch the port number to whatever you've signified, and then you could send that to the web server on your computer.
Okay.
Yeah.
And also you mentioned packets and frames. Could you like describe those?
Can I? Yeah, sure. Yep, no. So packets, again, this is where you get into education. It's like, oh shit, stuff that doesn't matter too much normally. So frames are a switch. So again, when you're thinking about, so even though switches are used in IP networks, they're not really IP networks. And so switches use frames. And so basically what the frame is, again, been a long time since I've actually studied it. It has the information for basically sending the stuff, and then it has what's called the payload, and so that'll be a certain size. So again, one of the ways you can increase speed, if you're looking at Cisco equipment, they'll have like jumbo frames. And again, don't quote me, it's been forever since I did my CCNA stuff. But basically, so the frames will be a particular size, and so it'll send, that much data, again, within the switch part of the network. Basically, that's a frame. Then you've got packets, and packets are kind of sort of the same idea for the IP world. And so that's going to be, basically the data is going to go in, it's going to have the header, it's going to have the to, where it's going to be going to, it's going to have the from information, it'll have some additional information, and the rest of this will be the data that's going. So basically, more or less, frames is switches, packets is routers, and again, if you want to get your CCNA, so much information on it, but yeah.
Thank you.
Yeah. Any other questions? No? Cool. Okay, well, that is the class for the night. We have the cybersecurity. So I will be doing the presentation at the All Things Open conference on March 23rd. March 25th, we're going to be back here. We're going to do cybersecurity for AI. So we're going to talk about some of the normal cybersecurity stuff and the AI stuff that goes along with it. Some of the interesting stuff there. We're going to have another class most likely on the 11th. I just have to get verified. So we are going to be moving. So March will be here. April will be at the Tobacco campus. So just like one block that way, much prettier, much nicer, much more wonderful, but it is a block that way. So at the 11th, I just have to get the approval because there's going to start moving. And so I just have to make sure I can do it. We're probably going to do Linux, so like an introduction to Linux class for that night. And that's what I got. That's what I got. Any final questions? Yeah. Cool. Okay. Remember, donor box exists. I will just say it exists.
Thank you, as always.
Yeah, yeah.
Great class, yeah. Also, these other papers, are these like, are you gonna throw these out or?
Yeah, you can take them. That's why I say any paper in there you can take. Yeah, basically all it is I put all the stuff in for classes, and if people don't take it, I just leave it in there, and then if you want it, you can take it. Yeah.